Okay, good morning. Welcome to day 4 of LXMLS 2016. I see that the banquet caused some casualties, uh, or maybe the after banquet, probably. So it is my great pleasure and I'd say pride to introduce André Martins, who's my colleague, former student for several, known him for 20 years now. He's a professor here at Instituto Técnico and a researcher at IT and a top name in Portugal, Europe, and the world in machine learning and especially in NLP. And he's going to tell us everything there is to know about transformers and large language models. Almost everything.
Everything. Okay, good morning, everyone, and thanks for coming here after the banquets and I guess for some of you the long night yesterday. Um, so before I start, let me just introduce my research team here at Technico. It's called Sardine, our lab. You can see that you have to be very careful picking the right letters to get Sardine in the end. For those of you who don't know, I guess some of you already found out, sardine is a very popular fish here in Lisbon. And in our group, we do a lot of research in topics like natural language processing, LLMs, sparsity, long context efficiency. Throughout this talk, I'm going to here and there mention some works that we are doing that are related to the topic of today's lecture. Okay, so it's funny to do this lecture now because if we go back 9 years ago, this was when the Transformers paper was published in June 12th, 2017. It turns out that we had a presentation at LXMLS shortly after. So this was roughly 1 month after the Transformers paper went to archive. It was not as popular as it is now by Fernando Pereira. The video is still available for those of you that who are curious. And it was pretty clear in this presentation that Transformers will be something very transformative in the next years. So you can see the slides and the video if you are interested using today's slides. Ah, está fazendo diferença. Deixa-me só pôr aquilo como. Ok. But yeah, so this is going to be the roadmap for today. So I'm going to pick on Noah Smith's lecture yesterday and introduce the attention mechanism. From there, the transformer architecture. Then I'll mention some of the current challenges with transformers, like how to handle long contexts, and a little bit of a discussion about what next. And this will be for the first part. Then we are going to have a break, and then I'm going to talk about LLMs in the second part. Okay, so what have you learned so far in these morning lectures in the school? So you started by hearing from Mario about linear models, everything about loss functions, and all these topics. Then neural networks with Biksha, and yesterday RNNs with Noah. And we saw that RNNs are particularly interesting because they are models that are very suitable to handle sequences because they can carry state information about that sequence. And briefly, Noah mentioned a little bit about some improved variants of RNNs that include some additional gating functions, things like GRUs, LSTMs. I don't think Noah mentioned Mamba and DeltaNet, but you can also see those models as recurrent models. And all these models have in common the fact that they, in their states, they carry what we can regard as some fixed size memory. So you can think of this as a vector that contains all the memory about the sequence that has been seen so far. Okay. Today we're going to depart from that perspective, and we're going to look at models that have a non-parametric associative memory, and I'm going to describe in a bit what that means. Okay. Okay, so let's start with the concept of associative memory. This is a memory paradigm that is inspired by the way the brain stores and retrieves information. And you can think of it as a memory that is based on content. So you can access elements of this memory by content, by similarity, as opposed to explicit physical addressing. Okay. And so there is this concept of content-based recall, which mimics, what neuroscientists thinks that happen in the brain when we see or when we hear a partial cue. This can trigger the recall of memories that are associated with the cue that is given as a stimuli. And so one class of models, which I would like to use as a teaser before jumping to transformers, one class of models that implements this idea of associative memory is upfield networks. How many of you know about upfield networks? Can you raise your arm? Okay, not many arms. That's interesting. So upfield networks is it was one of the very classical kinds of neural networks. In fact, 2 years ago, I think there was a Nobel Prize in physics given to Jeff Hinton and to John Hopfield, and the part about John Hopfield is precisely because of these kind of networks. In fact, the work of John Hopfield was predated by the work of Sunichi Amari in the 70s, who built a very nice connection between models from statistical physics and models for associative memory, and did the building blocks of what later became known as upfield networks. So I'm not going to get into a lot of details about upfield networks, but I want to use this as a little bit of a teaser because some things in upfield networks are concepts that are interesting to map to today's architectures. So in a nutshell, the idea is that upfield networks define an energy landscape where the minima of this energy function are attractors, and when you provide some Q and you want to retrieve some memory that is similar to that Q, then you are going to do several iterations, which means that can think of this ball as traveling through the energy manifolds until it reaches one of these attractor points. Okay, and these attractor points correspond to the patterns that are memorized. So in the training phase, we provide a bunch of patterns to the upfield network. The upfield network memorizes them. So it creates this energy function where the local minima correspond to those patterns. And then when we provide something that could be, for example, a corrupted version of this pattern or something that is similar to those things that have been memorized, there's going to be some updates, and eventually you are going to converge to a pattern like that. As you can see here in this example with the letter J, if we provide this as input, after a few iterations, we are going to converge to this minima that corresponds to the letter J. So mathematically, the way it works is, these are networks with D units. This should be lowercase d, fully connected. For those of you that are familiar with Boltzmann machines, there are some similarities between these kind of networks. We have a bunch of memory patterns that we used at training time, x1 to xn. So we are memorizing n patterns. And there's going to be a query, and there is going to be energy function associated with this query, which takes this form. It's not very important right now. And then there's some update equations that corresponds to these upfield dynamics, where we keep updating qt plus 1 based on the previous qt. The weights of the network are all the dot products that cross pairs of features in our patterns. And then it just happens that the memory patterns become attractors. Okay, this looks a little bit like magic, but let's see some concrete examples. Okay, so I picked here 5 of the LXMLS speakers of this year. You might recognize their faces. You might not have seen some of them yet, like Desmond is going to give the lecture tomorrow, but you'll see him. And Adele as well. So we provide these patterns at training time, and then at test time we give as inputs a query like this. You can see this is Adele's face masked, okay? And by running a few iterations, not many iterations, the network is going to provide this, okay? So I forgot to mention that, but these are images. We are basically flattening all these images to obtain a binary vector and feeding that to the upfield network. And if you do the same with the corrupted versions of the other patterns, it's also going to work very well. Okay, so we can have nearly perfect reconstruction. In Bix's case, there is a little bit of a degradation, not too much, but it's almost perfect. Okay, so it works pretty well. But now let's see what happens if we try to do this with all the speakers. Okay, so now we have 11, I think, 11 speakers in total, and we can do exactly the same thing. Okay, so memorizing all the patterns, and then running this upfield dynamics and see what's going to happen. So if you do that, the result is very disappointing. Okay, so you can see that you get a lot of Frankenstein speakers here that are weird mixtures of all the speakers. In fact, I think we can cluster these in maybe 3 different groups. these strange images are, you can think of them as some kind of averages of the other patterns. They are called metastable states in the optional network literature. And so what's happening here is that there is some capacity of the network to memorize patterns. If you go beyond that capacity, you start having a lot of interference between the different patterns. Okay, so this is showing a limitation that we have with this kind of networks, which is if we try to store too much information in a small number of parameters, at some point there's going to be interference, and you are not going to be able to retrieve this information. Okay, so in fact, there's a lot of mathematical studies of optical networks that quantify what is the capacity of them. I think in the best possible case, only 0.14 times D patterns can be memorized. D here is the number of features, so the number of pixels in those images. We are going to see later that optical networks are a little bit like linear transformers. Okay, don't worry if you don't know what linear transformers are. I'm going to talk about that in a bit. And in fact, there is a lot of recent work in recent years that try to modify the energy function of optical networks to increase memory capacity, to make them able to memorize more things. In fact, what this is doing is making these networks non-parametric, which they are called modern optical networks. Okay, and by making them non-parametric, this is starting to resemble more and more what attention-based transformers do. Okay. Right, so this was the short introduction that I wanted to give. If you want to know more about optical networks, there is a very nice web page here. I'm putting the link here that does a very good job at explaining what they are and what modern optical networks are. And I'm going to jump to the attention mechanism that gets a little bit closer to the topic of today's lecture. Okay, so let's go back to Noah's lecture yesterday and think again about RNNs. One thing that was mentioned in that lecture is that you can define a sequence-to-sequence model by combining two RNNs. Okay, so we can think of an encoder RNN. For example, let's suppose we are doing machine translation. So we want to map an input sequence to some output sequence. For example, translating from English to Portuguese. So we need an encoder RNN to encode the source sentence in English. Okay. So if we feed it through an RNN, it's going to produce some vector that corresponds to the end of sentence symbol. And then there's going to be a decoder RNN that we are going to use as an autoregressive language model. So you can think of this as a conditional language model, where at each step it's going to produce a word, and then that word is used as input to the next time step, and so on and so forth. Okay. And so this looks extremely basic, and it was quite amazing in 2014 when Ilias Sutskever and other people at Google presented this model. It looked, I could not believe that this could do machine translation, because there was so many years of research in machine translation before this that involved very complicated pipelines, systems that were super complex, and suddenly you have an architecture which is just two RNNs that are able to solve this problem. Okay. But still, this model was not perfect. It had some limitations. The main limitation is a little bit of a problem similar to the one that I mentioned about optical networks that highlights the problem that we can have when things start to interfere with each other. So one problem is that if you want to do a sequence-to-sequence problem, if you want to do machine translation, for example, you want the system to work for any sentence of every size, right? So we don't want to bound how big the source sentence needs to be. Okay, and for this example, it's just a small sentence with 3 words. Okay, so it's going to work well. But if you have a longer sentence, we are going to start to have a problem, which is the vector that is used to condition the decoder RNN is just a single vector, right? And this vector is going to become a bottleneck, because everything that is to be retained about the source sentence needs to be in this vector. Okay, so when we start generating the translation, we are not attending to anything in the source sentence anymore. We are just using as a starting point the vector that compresses that sentence. And vectors have a finite capacity, right? So there is a very famous claim by Ray Mooney, who is a very famous researcher in NLP, that says that you cannot really cram the meaning of a whole sentence in a single vector, which basically articulates the point that I want to make here. Okay. Um, so the solution for that was proposed in a very important paper in 2015. In my opinion, this paper is more important than a transformers paper because it brings the main ingredient of transformers, which is the attention mechanism. And the idea here, okay, so maybe we should not encode a sentence as a vector because you are going to have this bottleneck problem, but instead as a matrix which can grow with the size of the sentence, right? So if you have a matrix where the number of columns correspond to the number of words of the source sentence, then for longer sentences we can have a longer matrix, and maybe we can do a better job that we can do with this vanilla sequence to sequence model that I was showing before. And so the way it works is we encode the sentence as a matrix, and then before generating each word in the decoder autoregressively, we use something called an attention mechanism that is going to condition on the relevant source words only. Okay, so this is trying to mimic a very important idea in machine translation before neural networks called alignments, where we want to align the word that you're going to generate with the words that exist in the source language. Okay, so you can think of attention mechanism as some kind of soft alignments. And so this was really what opened the door for the transformer architectures that were proposed 2 years later. Okay, there is also work done more or less in parallel by a team at Meta. So this paper by Badana was from Mula, so an academic lab. At Meta, they were working on something called end-to-end memory networks that were more or less the same idea. Okay. So let's see how it works when we bring attention mechanisms to RNNs. So we start with the sentence that I was showing before. We pass it through an RNN. This is going to produce encoder states H1, H2, H3, and we obtain a decoder state. Let's call it Qt, because it's useful to think of this decoder state as a query when we bring the attention mechanism. And then the next step is we are going to compare these decoder states, this query, we are going to compare it with each of the encoder states, H1, H2, H3. Okay, I'm going to get into more details about how this comparison is made later on. And so as a result, we are going to obtain three numbers that we can interpret as some kind of association score between the word that you want to generate now and each of the source words in the original sentence. Okay, so these are going to be three real numbers. And we want to map these numbers to a probability distribution. Okay, so what is the way to map some real number to a probability distribution? Anyone? Most common way. Sorry? Sigmoid, yes, if you want a single probability number. If you want to do this with several numbers, it's a softmax, right? So we just do a softmax transformation of this vector of scores. And this is going to give us an attention probability to each word. We can interpret this as how much we need to focus on each of these words to generate the next word that you want to generate. So in this case, the next word is going to be the first word of the translation. And these probabilities tell us that we should look at love and I, okay? And as a result, we are going to obtain a vector. This vector is going to be a weighted average of these encoder states, weighted by these probabilities. And as a result, this is going to generate the word adoro in Portuguese, which is the first person present tense of to love. Okay, so this is attending at I love and to generate the Portuguese form. And then because this is an autoregressive model, we provide adoro as the word in the next time step and repeat the process. This time we're going to attend more on the word Lisbon. So this weighted average is going to be very concentrated on this vector. And as a result, this is going to generate the Portuguese words for Lisbon. And later it's going to generate the end of state and we are done. Okay. Any questions about this process? Who has seen this before, just to get an idea? Okay, so this is not news for a lot of you. Good. So this paper was originally targeting machine translation. And so they showed some plots where they were translating from French to English, and they examined where the attention probabilities were going for every word in the targets that was generated. And things kind of made sense, right? So this looks like a soft alignment. So for example, if you look at European Economic Area. Okay, so in French, you invert the order of the words. You say Zone économique européenne, and as a result, these colors tell you that when you generate area, this is attending zone, and so on and so forth. Okay, and they have a lot more examples in the paper. So the interesting thing is that we can apply this idea not just to sequence problems, but anything to a sequence. For example, caption generation. Now the input is an image, it's not a sequence anymore. But you can also do attention over images. So attention works not just with text, but with arbitrary objects. And what they observed is that, for example, here, when you are generating a caption for this image, when you generate the word frisbee, the model is attending to the object frisbee in the image. Okay, and similarly, when it generates dog, it's attending to the dog, and so on and so forth. Okay, this is very interesting. Okay, so to wrap up and to introduce some of the notation that I'm going to use in the rest of the lecture, we need to have in the attention mechanism, we need to have some query vector. In this case, the query vector was the decoder states corresponding to the next step of generation. We need to have some input vectors. This corresponds to the encoder states that we have in the source sentence. Let's call them H1 to Hn. We can put everything together in a matrix H, capital H. We need to compute association scores by comparing the query with these input vectors. Okay, I'm going to tell you later how we can do this, but this is going to result in real numbers S1 to Sn. But because we want probabilities and not real numbers, we use a softmax transformation to convert these scores to probabilities. As we have these probability vectors, we do a weighted average of the input vectors, which you can write in matrix notation as H transpose times P. And this is going to give us a new vector that is, you can think of it as a view of the inputs, but focusing on the important parts. Okay. So let's take a closer look at some of these steps. So let me go to this step where we need to compute the association scores by comparing the query with H. There are several ways in which this can be done. In the original attention paper by Badanal, they did it in a way that was too complicated, actually. So they had like a small feed-forward network where HI, so each of the input vectors that they want to compare against, and the query was provided as inputs of this small feed-forward network. And they had to learn these parameters in red, and as a result, they got a score back. In later work, they simplified this, and they just did this by doing a dot product or a weighted dot product between the query and key. Okay, I'm calling key to this input vector. This is going to make sense in a bit when we talk about keys and values. But yeah, it can even be simpler than that. It can just be a dot product attention. If you just compute the dot product between the query vector and the key vector. Okay, so Q transpose HI. Of course, this only makes sense if the two vectors are in the same embedding space, right? And in some cases, you can guarantee that. So the one advantage of the last two formulations is that they are much more amenable to parallelization. So if you want to compute, using our GPUs, doing some parallel computation, if you want to compute the similarities between a query and all the input vectors in parallel, we can just turn these into a matrix multiplication, right? You can just do H transpose times Q, and you get all the scores at once. And in this case, that will be a little bit more difficult. Okay, so so the second point I want to make is that in the formulation that I described so far, we are using you are using H in two places, right? We are using it to compute these association scores, where we compare H with Q, and then we are using it later to do this weighted average. Okay, but in fact, we can actually do it differently. We can have separate vectors for these two operations. We can use them. You can use the keys You can use some representation of these vectors as keys in the comparison with the queries, and you can use some representation of these as values to do the weighted average. Okay, so I'm going to, from now on, I'm going to assume that they don't need to be the same. Instead, we're going to have some key matrix K that contains key vectors associated with each of the things that we want to attend to, and we have a value matrix of the same dimension. Maybe it can have like a different representation size, but n is the size of the sequence, is the same for both, and the value matrix is going to contain the values. Okay, this is just more general. Okay, so it's useful also to think about attention as some kind of soft lookup table. Okay, so in a classical lookup table, you have a table of keys that map to values, and a query is something that is going to exactly match one of the keys. When it matches one of the keys, you just retrieve the corresponding value. Okay, this is what lookup tables do. Attention is similar, but it doesn't require us to match things exactly, right? So instead of having this hard match, we can have a soft match. Okay, so the query is going to match to all keys, but it's going to assign some probability to each of the keys. There's going to be certain keys that are more similar to the query than others. And so as a result, we are going to have some number between 0 and 1, which is going to be the attention probability associated with those keys. And then the values are going to be multiplied by those corresponding weights and summed. Okay, so if it happens that the attention is very peaked towards a particular key, so if there is almost zero weight to a lot of keys except, let's say, K4, then this is going to become equivalent to a lookup table. Okay, but you can think of it as a soft version of a lookup table. Any questions about this? By the way, feel free to interrupt with questions anytime. Okay, this is nicer if it's interactive. Okay, so here's the full general version of what I've described so far. Now we are going to assume that we have a query vector queue. We are going to have key vectors and value vectors that don't need to be the same, K and V. We are going to compute query key association scores. And then we are going to convert these scores to probabilities, and then we output a weighted average of the values. Okay, so this is a more general form of attention than the one that was used in Badano. Okay, so far we talked about attention with RNNs, and this attention is what is called contextual attention, because we are, the decoder state is attending to the encoder states, which you can think of as part of the context. But we can also do something called self-attention, which is going to start getting closer and closer to transformers. Okay, and so one interesting point about attention that explains why it works so well is that it allows focusing on arbitrary positions in the source sentence. So if you think about the computation graph that is generated when we introduce the attention mechanism in an RNN with attention compared to the vanilla RNN encoder decoder, this attention is shortcutting the computation graph, because when you are generating, let's say, the word Lisboa, which is the Portuguese translation of Lisbon, the model is putting a lot of probability to the English word Lisbon, and therefore it's going to create a shortcut that attends directly to that word. Okay, so this is an idea that is very powerful, and that's why it works so well. When we are backpropagating gradients, we receive gradient signal coming directly from this path. But so people start thinking, okay, if attention gives access to any state, if we don't need to propagate the state sequentially, as we typically do with an RNN, do we really need the RNN? Can we just use attention everywhere, right? That was what triggered interest in developing something like the transformers. So we are going to see that one alternative to an RNN is to use something called self-attention, where at each position, the encoder is going to attend to the other positions in the encoder itself. So this is no longer the decoder attending to the encoder, it's the encoder attending to itself. And you can do the same thing on the decoder side. When we are generating the sequence, we can also have the decoder attending to the decoder representations directly. Okay? So this is what a self-attention layer is going to look like. Let's assume that we are working with a sequence of size n, I'm going to stick with this notation. N always means the length of the sequence. So now we can have a matrix Q, a query matrix. Okay, so every column corresponds to a query that is associated with an item in that sequence. We have key vectors and we have value vectors of the same size. And now we are going to compare every query with every key. Okay, so this is what self-attention is doing. Every position with every other position. So we can do that as a matrix product, right? So you can do that as Q times K transposed. Okay, so when we do that, we end up with a matrix n by n. So n again is indexing the position of the sequence. So this is a score matrix that contains how similar is each token to every other token. And then we need to convert these scores to probabilities, okay? And we are going to do that row-wise, okay? So we are going to apply a softmax to every row of this score matrix, okay? And finally, we are going to output the weighted average of the values, but you can write the entire thing in matrix format, right? Because you can operate with all the rows simultaneously. So we can write this weighted average as the matrix P, a matrix where the rows are probabilities, times the matrix V, which is the value matrix, okay? And as a result, we are going to have new representations for this sentence, which are going to be n times the dimensionality of the values. Okay, so if you put everything in the same expression, we end up with this expression. So we have the softmax of Q times K transposed. This is giving us the probability matrix times V. Okay, and I'm going to come back to this expression several times in a bit. Okay, so this is precisely what the transformer papers did with some subtleties. What's going on with the sound? Okay. There are some subtleties. There is some feedback. I don't know where it's coming from. There are some subtleties that I'm going to mention in a bit. But if you do that, if you do this self-attention, is the mic working? Okay. If you do this, then you can, you know, for a sentence like the one that is shown here, you can see how much each word in this sentence attends to every other word in the sentence. Okay. You can think of this as some kind of self-alignment. Okay, any questions before I proceed to the transformer architecture? So this is the main, yeah?
How do they correspond and how do they differentiate the values?
Yeah, so for now I'm being agnostic about how you compute the keys and values. I'm going to talk about that next. For now, I'm just assuming that we have some way of getting keys and values and we are using them differently. So keys is something that we use to compare with the queries, right? And values is something that once you already have the attention probabilities, we use it to obtain the weighted average. Any more questions? Yeah.
Thank you. Starting from the previous point from the attention, I didn't quite catch how the order of the word is preserved, and also here. Like
Yes.
in the translation part.
Excellent question. I'm going to come back to that in a bit. Okay. So the short answer is that it's not preserved. And then I'm going to explain what we do to take into account the order of the words.
Thank you.
Okay, there's another question in the back. So the similarity is in this step, right? So this is where we are doing all the dot products between queries and keys, right? So it results in a matrix n by n because we are comparing every word with every other word. Yeah.
Do queries after the first generation also keep the ones newly generated, or do we just keep the input queries?
Yeah, I'm going to explain the details about that when we have several layers of these. I think that's what you're asking, right?
Yeah, because in the translation case, do we also keep the the newly translated word also in the query for, let's say, the the second translated word?
Okay. So in the decoder side, when you are generating autoregressively, yeah. So as you generate more words, you provide those words as input, and you attend to the words that you have generated so far.
That's the new columns then, or?
That's going to create new columns. Yes.
Okay. And
Yeah.
how do or how does the fixed row size work? Do we know that's the maximum amount of letters a word can have in our?
So as you generate more words, the number of columns is going to increase, right? So you don't need to, unless there is a, typically there is a computational limits, right? But ignoring that, there's usually a maximum size.
Yeah.
But ignoring that, things can be incremented one
Thanks.
after the other. Yeah. Okay, so I'm going to proceed. A lot of these questions, they are going to be answered in a bit. Okay, so hopefully that is going to make more sense when I present the full architecture. So this is the famous picture that many of you might have seen in the Transformers paper called "Attention is all you need." And so the key idea is this: is instead of RNNs, just use self-attention in the encoder, also in the decoder. Each word state is going to attend to all the other words. It's not just self-attention. So in fact, there is a feed-forward transformation that follows. This is basically a feed-forward network that is applied in parallel to all the words in the sequence, sharing the weights. Okay, and we do several layers of this. Okay, so we have several blocks, and blocks. And we do the same thing for the decoder with some small differences that I'm going to explain in a bit. With the difference that in the decoder we attend only to the words that have already been generated. We cannot attend to the future words, right? And I'm going to describe later how we can ensure that. So there is a very nice place that illustrates every single operation in Transformers, which is J. Lamar's blog. Maybe some of you have seen it, called the Illustrated Transformer. I'm taking some materials from this piece. But so this illustrates the idea, okay? So in the original Transformers paper, they had an architecture with 6 blocks, 6 encoder blocks, and 6 decoder blocks. When we provide a sequence as an input, it goes through all these encoders. Each of these things involves several self-attention steps. And then when we start generating the outputs, we go through several decoders, and you also have attention from these decoders to the encoders, the same way as we use attention in RNNs. Okay, and I'm going to illustrate each of these blocks next. So each encoder block has 2 layers, a self-attention layer and a feed-forward layer. In the decoder, there is an additional encoder-decoder attention. This is to attend to the states that come from the encoder. And inside these, you can, so let's assume a very simple example. It's always easier to understand things with very simple example. Let's suppose that your input sentence only has 2 words, thinking machines. Okay, this was the example in J. Lamar's blog before the company Thinking Machines existed. And so the first step is to go through self-attention. This is going to result in new representations, Z1 and Z2. And then these are inputs to a feed-forward neural network, and this is going to result in R1 and R2. And then in the second encoder block, we repeat the process, right? We do again self-attention and feed-forwards. And you can see that this feed-forward neural network is the same network applied in parallel to the 2 words of the sequence. Okay, so let's look closely to each of these operations. So one of the questions that was asked before, just a few minutes ago was, what is the difference between the keys and values? How do we make sure that they are different? So this is ensured by using different projection matrices. So we start with embeddings of the words. Okay, if you recall the previous lectures where they described word vectors or word embeddings, X is the matrix that contains the representations of the words thinking machines. Okay, it's 2 by 4 because we have 2 words in a sentence. The first row is the embedding of thinking. The second row is the embedding of machines. In this case, just 4-dimensional embedding space. In practice, it's more than 4, right? This is just for illustration purposes. And what we are going to do is we multiply these embedding metrics by a projection matrix. Okay, so there's going to be separate projection matrices for the queries, for the keys, and for the values. Okay, and after this multiplication, we are basically reducing dimensionality. We are projecting the embeddings to a lower dimensional space. In this case, 3-dimensional. Okay, so the projection matrices are 4 by 3. And this is going to result in a query matrix, a key matrix, and a value matrix. Okay, so mathematically, we can represent these operations like this. Okay. And these things are all model parameters. Okay, so they need to be learned from data. They are parameters of the neural network. So this is it. Okay, so for our concrete example, we have the embedding for thinking, the embedding for machines. We use these 3 projection matrices, and as a result, we're going to obtain a query vector for each of the words, a key vector for each of the words, and a value vector for each of the words. Okay. Any questions? Yeah. So these matrices are parameters of the neural network. We are going to have a loss function, which is going to be similar to the loss function that we saw, for example, in the RNN's lecture. It's going to be a cross entropy loss for every word that you are generating. And then you just backpropagate, right? And as a result, you are going to update the weights of the network, which include these 3 matrices, to try to assign as much probability as possible to the examples that we are providing at training time to the network, right? So very classical neural networks. We treat it as regular parameters. Does that answer your question? Okay, so next there's 2 transformer innovations that are worth presenting. One is scale.product attention. The other one is multi-head attention. So the scale.product attention is, before I add this expression, softmax of q k transpose times v. But in fact, what is done is there is a small thing that is added, which is dividing by the square root of the dimensionality of the keys. Okay, why is this done? So the main reason for that is as the dimensionality of the keys gets large, and because people try to scale these models, they make these dimensions larger and larger. The variance of the dot product between the queries and the keys, which is our association score, it's going to increase. And as a result, the softmax is going to become very peaked, because you are basically creating a score vector that contains very large values. If you do a softmax, if you apply softmax at a vector with very large magnitudes, is going to become very peaked. It's going to result in something very close to a one-hot vector. Okay, so it's necessary to do some scaling by the dimensionality of these vectors. And people came up with the square root of d, which might look a little bit mysterious, but in fact, there is a good explanation of why square root of d. Okay, so, and I need to bring some basic statistics to explain the reason. So if you have any pair of random variables, let's call them x and y, and any coefficients a and b, you can write the variance of these, ax plus by, as this expression, okay, where we use the individual variances of x and y plus the covariance between x and y. Okay, so if x and y are uncorrelated, which is going to be the case if they are independent, but not the other way around, this covariance is going to be 0. Okay, so basically the entire thing reduces to a combination of the variances, where we get a squared and b squared as the coefficients. So now let's think about our concrete case. We have queries and keys, and the dot product between the query vector and the key vector is going to be the sum of the products of the individual features, right? And let's assume, and this is a big assumption, but it just helps us doing these design choices. Let's assume that they are all uncorrelated, and let's assume that the variance of each individual product is fixed and it's sigma squared. Okay. For example, if you make these samples from a Gaussian distribution, we can use this variance as the variance of the Gaussian. So, so then in that case, the variance of Q transpose K can be written as the variance of this expression. And by using this formula, this becomes D times the variance of an individual product. And because we posited that this variance is sigma squared, this becomes d times sigma squared. Okay. And now using this expression, this means that if we compute the variance of this divided by the square root of d, the total variance is going to be sigma squared. So it's going to be independent of d. Okay, so basically we are ensuring by dividing by the square root of d that the variance is not going to increase or decrease with the dimensionality. Okay, so this is basically the reasoning that led to the square root of d. That and of course some empirical work to see that it works. Because this assumption that they are uncorrelated and have a fixed variance is a bit of a stretch. Okay, so this is scale.alert attention. The second innovation that is worth talking about is multi-head attention. We didn't talk much about convolutional neural networks in the school. How many of you learned CNNs at some point? Okay, several of you. That's good. So when you learn about CNNs, you learn about filters, right? And how usually CNNs are applied with multiple filters or multiple channels, right? So multi-head attention is basically building on the same intuition. Okay, why do you just want a single attention transformation? Why don't you have multiple channels where we are applying attention transformations using different projection matrices to obtain queries, keys, and values? Okay, and it's useful to think about this connection between convolution and attention because to me, attention is very similar to a convolution, but where the filters are, where the filter weights are not learned, but are adaptive to the inputs, right? You can think of an attention mechanism as a 1D convolution that has infinite width, so it spans the entire sequence, and where the weights are not fixed, but rather that depends on a query and what is the similarity that you want to give to the different keys, okay? In fact, this idea was there a long time in signal processing, much before attention mechanisms have been proposed. Okay. Okay. So the solution to this is multi-head attention. Okay. This is attention with multiple channels. In the original Transformers papers, the paper they used 8 attention heads. So I'm going to use H to denote the number of heads. There's going to be specific projection matrices for each head. And we just apply attention in parallel on the different channels. And then we need to combine everything together. This is done by concatenating the outputs of these different attention heads and then piping through a linear layer by introducing an output projection matrix called WO. So it's easier to understand this with an example. Okay, so let's go back to JLMR's blog. So same sentence, thinking machines. Okay, this matrix X, 2 rows, 1 for each word. So we are going to have 8 heads. So this means that we are going to have 8 triples of queries, keys, and values weight projection matrices. By doing these projections, we obtain triples of queries, keys, and values for each of the channels. By doing the similarity and the softmax and the weighted average with the values, you are going to obtain representations Z0, Z1, and Z7, like 8 different representations, 1 for each head. Okay, and the dimensionalities of these things are going to be the dimensionality of the queries, keys, and values that I'm assuming that it's the same for all these 3 things. So we're going to have matrices 2 times 3. Okay, so now you concatenate everything. So this means that we are going to obtain a new matrix which is 2 by 24, right? Because it's 3 times 8. So we have like a 2 times 24 matrix. And we need to multiply by another projection matrix, WO, that is going to restore the original dimension of 4 that matches the embedding size of the original tokens, okay? And now our final Z is going to be 2 by 4, okay? So same dimensionality as X. This is one block. The next step is this is going to be given to a feed-forward neural network. It's going to, the output of the feed-forward layer is going to be R. And in the next block, we are going to repeat the process, self-attention plus feed-forward layer. But instead of using X, we are going to use R, right? But you do the same thing. You multiply R by all these projection matrices. We obtain these for every head and so on and so forth. Okay. Any questions? Okay, good. How many of you have seen JLMR's blog before? Okay, that's good. It's a very nice explanation. So there's several other tricks. So in the original transformer papers, they had two versions of the model, one with 6 self-attention blocks and another one with 12 attention blocks. Next, I'm going to talk about 3 other things: positional encodings, residual connections, and layer normalization. So let's start with positional encodings. There was a very good question asked a few minutes ago about how do we make this dependent on the word order. In fact, with what I have described, the transformer encoder is equivariant to the word order, right? It's going to be insensitive to the word order because attention is not, you know, it's when you are comparing a key with a key, we are not looking at what is the actual position where this key came from. So if you want to make it sensitive to order, we must add positional encodings, okay? And the way this is done is by getting our word embedding. Let's call it x1, x2, x3 for this 3-word sentence. And we are going to have also an embedding for the position, t1, t2, t3, and you just add the 2, right? So we just add x with t. You might wonder, but isn't that going to cause a lot of interference between the positional encodings and the word embeddings? It does, but in practice, this interference is not too big. So people just stick with this solution, okay? And that's it. So the embedding that we are providing to the transformers, the thing that I was calling X before, in fact, it's a combination of the word embedding with the position embedding, okay? And by doing that now, we are encoding the position in this system. Okay, does that answer your question? I don't remember who asked. It was somewhere on that side, I think. Okay. So how do you obtain these positional encodings? There are several possible strategies. The simplest one is let's just learn one specific embedding vector for every position. But to do that, we need to specify a maximum number of positions, right? So it has a disadvantage that it's not going to work past that sequence length. The other strategy, which was the one used in the transformers paper, is to use sinusoidal positional encodings. I'm going to present that in the next slides. The current solution that is more common nowadays is to use relative positional encodings. So sinusoidal positional encodings, the idea it goes like this. So instead of learning an embedding matrix as a parameter when you are learning the network, you just use you just encode the embeddings for every dimension of this embedding vector by using sine and cosine functions with different frequencies. So here I'm showing like 4 different frequencies for sines and cosines. And the x-axis is going to correspond to the position in the sequence, you know, from 0 to 100. So if we slice these in a specific column, okay, so if you pick a specific position, there's going to be a specific signature for that position, right? So we are going to be able to produce positional encodings that are going to be different from different positions. But there is another property that is interesting, which is they are going to vary smoothly across nearby positions. So the embedding for position 16 is going to be similar to the embedding for the position 17, but slightly different. So the model is still going to know the difference between these 2 positions, but it's not going to be completely different, which could be the case if we learn the positional encodings as additional weights. And using a mix of low and high frequencies is good because you can capture some of these embedding dimensions, can capture more global phenomena, like are we in the beginning of the sentence or in the end of the sentence, and other dimensions can capture something a little bit more granular. So this was the solution that was proposed in the transformers paper. More recently, a problem that was still a bit tricky to solve with these absolute positional encodings, where the sinusoidal are a particular example, is that they are hard to scale to arbitrary context lengths. And in the years that follow transformers, people start increasing more and more the context length. And it was more convenient to look at the difference between the distance between 2 tokens, the relative distance, as opposed to the absolute position in the sequence. And so one way to do that is when you are computing the association scores between queries and keys, you can add some coefficient that is going to depend on that distance. Okay. So one particular case of relative positional encodings that is a little bit more intricate than what I'm describing here is rope or rotary positional encodings that combine both these absolute and relative position information. Okay, so I'm not going to get into a lot of details about these positional encodings. They are used in most transformer models that are released these days. The fundamental idea is that you pick consecutive dimensions in your embedding space, and they are going to define rotations. And the angle of this rotation is going to be dependent on the position in the sequence. Okay, so if you are in position 100, it's 100 times some base angle. And then when we are doing the dot product between queries and keys, this is going to look at what is the relative angle by which we rotated the corresponding queries and keys. Okay, so it's more or less like this. Okay, so another important thing in transformers that departed from previous models is using residuals and layer normalization. So if you look at the famous picture in the transformers paper, they have this add and normalize layer there. And now I'm going to describe what this layer is doing. Okay, so what this layer is doing is basically recall that before self-attention, we had embeddings forming a matrix X. Then we did self-attention with multiple heads, and we obtained Z, right? So when you learn about feed-forward networks, you learn about layers being, following each other. So you would expect Z to be the inputs for the feed-forward layers. But in fact, what's done is we sum Z with X. Okay, so there is going to be a skip connection here that takes the original word embeddings, skips the self-attention layer, and is going to sum to Z. Okay, and then we are going to sum the two things, and we're going to apply another operation called layer normalization that I'm going to describe in a bit. Okay, so let me start with the residual connections because there's two ideas here that are entangled to each other. Residual connections became very popular in computer vision with ResNets. So those of you who learned before about CNNs might have learned about ResNets as well. As networks started to be very, very deep, training started to become quite unstable. So if we take a vanilla feed-forward neural network without skip connections, the loss landscape looks more or less like this, okay? But if you add some shortcuts, if you add some residual connections similar to the example that I was showing in the previous slides, this is going to have the effect of smoothing the loss function landscape, okay? And as a result, optimization is going to be much easier, and it's going to be easier to learn the parameters of the network. So this idea is actually older than ResNets. Similar ideas go back to Sepp Oschreiter's PhD thesis in 1991. And even earlier, I think people have already thought about this problem. And transformers just supported this idea, building on the success of ResNets by introducing these skip connections. In fact, if you remove these skip connections from transformers, you are going to see that learning is much harder. So the second idea is layer normalization. So the idea here is, following a series of works, people realize that we can accelerate convergence by trying to remove uninformative variation in layers. Okay, so let's suppose, and this is not specific to transformers, right? You can use it in different architectures as well. So let's suppose that at some point in your network, you compute H, your hidden layers. So the idea of layer normalization is you compute the mean of that layer. I'm calling it mu, and you compute the standard deviation. And then we do a transformation where we basically subtract the mean and divide by the standard deviation, okay, with some epsilon to make things a little bit more stable. Because for cases where the standard deviation is close to 0, this can create some numerical problems. So it's common to use a small epsilon here to make things a little bit smoother. And then you can also make it a little bit more customizable and multiply these by some learnable weights and add some bias. Okay, so gamma and beta. You should not worry too much about this. You can assume that this is 1 and this is 0, so you only have this part here, for simplicity. And in fact, this also makes convergence faster. More recently, people simplified this even further. So they removed the mean subtraction. So there is this thing called RMS norm, which I think is also the default in most modern architectures. We remove the mean subtraction, so we are just doing L2 normalization. We are just dividing by the norm of H, okay, with some epsilon. So there's also a few things after the transformers paper that the people played with. So one is in the original transformer, layer norm was placed here. So we do multi-head attention, then we add that to the original embeddings. You can think of this gray area as the residual stream. Okay, so you can think of these as on the side we are learning some transformations that we are going to add to the original word embeddings, but there is a part of these vectors that gets propagated further and further, right? This is what happens when you use residual connections. And so initially, in the transformers paper, the add and normalize operations were performed here. Later, people tried to move layer normalization to a different place here. It seems to work a little bit better. So I think now you have some architectures that use the solution in the left, post-normalization, others use pre-normalization. Yeah, so there's some small differences depending on which architecture we are using. Another small difference compared to the original transformers paper, in the feed-forward layers, in the original transformers, they used the ReLU activation. So it was a two-layer feed-forward network with a down project operation and a up projection, and the nonlinearity was a ReLU. Later, this was replaced by something called Swiglu, which magic done by Noam Shazir, which basically is, you can see it as a gated linear network. So this is a linear network. And then there are some gates that are controlled by a swish activation, which is something that looks similar to a ReLU, but it's differentiable everywhere. So a little bit more stable than a ReLU. So this is also what you find in most transformer implementations for today's LLMs. Okay, so far I talked about the encoder, but you also have the decoder, right? And so what's different there? So everything is pretty much the same as the encoder. There's only two things that are important to mention here. The first one is a very obvious one. The decoder cannot see the future, right? We are using the decoder to generate tokens autoregressively. So we cannot condition on future tokens that have not been generated yet. So when you are training the transformer and you have the complete output sequence that we want to use to obtain perplexity or cross entropy loss, we need to mask the future tokens to make sure that the model is not attending to any information coming from the future, right? So this can be done by using something called causal masking. I'm using quotes here because, causality is a big topic that we're going to learn about tomorrow in Adele's lecture. So this has nothing to do with that kind of causality, but it's something that forces the model to work in a left-to-right fashion and not looking at the future. So this is one difference. The second one is that the decoder attends not only to itself, not only to the tokens that have already been generated, but also to the input tokens, to the encoder states. Okay, this is the contextual attention, and this part is very similar to when I describe attention mechanisms with RNNs. It's basically states attending to states that come from the encoder side. Right, so this is in the famous transformers picture, the masked multi-head attention. This contains the causal masking that I was mentioning before. This ensures that the decoder self-attention, you only look back, you only look at the past, you don't look at the future when you are computing self-attention. And the context, so this can be done with a causal mask that looks like this. Okay, in PyTorch, you would use this masked fill operation. So basically what you do is to provide minus infinity logits so that when you do the softmax, you're going to have zero probabilities, which is the same as ignoring those tokens in the future. And for the context attention, it looks like this, right? So in every layer of the decoder, we are going to look at the last layer of the encoder. And so it's going to be attention similar to the one that I described in the beginning of the lecture. There's of course many more things with transformers. So the transformers paper, it took a lot of work. So this was done in Google, and it took them, I think, around 1 year to get everything together. There was a lot of engineering being done. It was not an architecture that worked at the first attempt. So they knew what they wanted to do. They wanted to replace RNNs by self-attention. But there was a lot of devils in the details, right? So one thing that was changed as well was the optimizer. So they used Adam, which is a commonly used optimizer, but they had these warm up steps where we start increasing the learning rate in the beginning, and then you start decaying this learning rate afterwards. And we didn't have this in earlier models before transformers. Okay, and it was actually quite important to make learning works. So more recently, there is this field of optimization with neural networks have been revived. For example, recently there is a new optimizer called Muon that some of you might have heard of, that some people are using, which might compete with Adam. Adam is already very old. I think it's more than 10 years old. It's a paper that has 1 million citations or something. What? Quarter million. So yeah. So that's because every time you write a paper and you explain your experimental details, you always say, we used Adam, and then you cite the paper. So that accumulates a lot of citations. But so the overall story here is that transformers are much harder to optimize than RNN sequence-to-sequence models. So before transformers, we used to use BILSTMs, which is RNNs with some gating functions. And one amazing thing about these models is that it was very easy. You didn't have a lot of hyperparameters. It was very easy to make them to work. With transformers, we need to be careful with a lot of things, right? They will break if you are not careful. You need to tune your hyperparameters and so on. Of course, in almost 10 years after transformers have been proposed, the field matured a lot. So now you don't need to tune hyperparameters every time you turn transformers. You can inherit with other people did before. But they are much more brittle than RNNs. But they work much better. Okay, so this is a table of results coming from the transformers paper, where they run experiments in machine translation, English to German and English to French. They were comparing with a bunch of different things. Apart from RNNs with attention, people also tried convolutional neural networks instead of RNNs to parallelize the computation, and transformers outperform all that. Okay, so they got very exciting results. We can also have some interesting information coming from the attention layers that give you some interpretability about what the model is doing. So they noticed that some attention heads seem to look at some syntactic phenomena. For example, ear making more difficult. More difficult is like a syntactic argument of making, and that there seems to be that some attention heads are focusing specifically on those things. Some other attention heads are looking at an AFRA resolution. In this case, the word "its" refers to the law, right? And there is some attention head that is speaking on those things. But one of the things that are more relevant in transformers, and this was the reason why Google cared so much about developing this model, is that they are much faster to train. So they can save a lot of flops by training transformers compared to RNNs, because RNNs, if you think about it, you need to do a lot of sequential computation, right? To compute the next state given the previous states. It's not parallelizable. Convolutional neural networks are parallelizable, right? So if you learn about them, you can compute all the filters in parallel. And in transformers, attention is also parallelizable, right? You can do all the computation in the different positions of the attention, the different ads. All of these can be parallelized. So this means that training can be much faster if you have GPUs that enable that parallelization. But they didn't highlight that so much in the paper, but decoding becomes more expensive because now it's going to scale quadratically with respect to the sequence length. Okay, so with RNNs, it scales linearly, right? Because every time you generate a token, you update your states, and you are always attending to that state. But in transformers, for every token that you generate, you have to attend to all the previous tokens that you have generated already, right? So this becomes quadratic. And this is going to be problematic for long sequences, okay? And this is going to be the topic of what I'm going to present next. Any questions before I jump to the next part? Let me look at the time. No questions? Okay, so handling long contexts. So I already mentioned this idea of memory and how important it is to link that to transformers, because transformers is like a non-parametric associative memory. If you think about modern LLMs, having some memory of past interactions is very important. So long-term memory is something that we should think about. So there's many applications that require long contexts. For example, think about software engineering tasks where we need models that look at an entire repository, which can be quite big. Or if you are solving an extremely challenging math problem, for example, in the last few days, there was like some proof of the Jacobian conjecture, right? That was done by an LLM. So solving problems of that kind require a lot of tokens being generated, conditioned on prior attempts, trial and error. You know, if you start doing reasoning, then your context size is going to increase substantially. If you want to use AI for scientific discovery, the same. If you want to condition on personalized chat interactions on very long histories, you are also going to have this problem. If you want to deal with multimodal data, for example, if you want to condition on videos, okay, long videos, representing videos as tokens consumes a lot of tokens. So we need ways, if you want to use transformers, you need ways to overcome these problems. And in fact, I would say that today we are abusing transformers. We are not using transformers, we are abusing them, because using a transformer to process context sizes beyond 32K, it's not really a scenario where transformers have been designed for. So, a lot of new architectures are emerging because of this problem. So I'm going to talk a little bit about that. For context, this is like a typical document length that you see in various kinds of data. So the idea of making transformers more efficient has been there for a long time. There is a very nice survey from 2022. It's a bit outdated, but I think the fundamental ideas are the same. They are still there. That describes different methods of different flavors to try to make transformers more efficient when they need to process long context information. Yeah, I recommend you to take a look at this survey if you want to see more information. So I'm highlighting some of the proposed solutions that have been considered, some more successful than others. So one is flash attention. Flash attention has been a big success. I'm going to talk a little bit about that. It's not a very creative solution, maybe, like it's not modifying anything in the attention. It's basically focusing on how to make the computation efficient by exploiting the hardware properties of GPUs. Then we have lots of approaches that try to sparsify attention or to use sliding windows in the attention to avoid having to look at the entire context. Group query attention, hybrid architectures, dynamic sparsity, which includes some work done by our group, hierarchical attention, and so on and so forth. So I'm going to mention briefly some of these in the time that I have left, which I think should be 10 minutes before we do the break. So let's start with flash attention, which I think it was the most successful of these techniques. If you look at, so this plot is interesting. So this is showing between 2018 and 2025, so not very far from today. What was the context length supported by models that were released, okay? And you see that until July 2022, the context size was quite stable at around 2K, okay? So a bit less, a bit more, but we didn't progress much from 2K tokens, which for today's standards, it's nothing, right? 2000 tokens is very small. And then something happened here, and there was like an exponential increase. This is in log scale, by the way, right? So Llama 4, for example, supports 10 million tokens, right? So there is a big jump from 2K to 10 million. And so a big part of this has been enabled by flash attention, work by Treat-Ao and other people, which managed to reduce memory from quadratic to linear. Okay, so the runtime is still quadratic. Okay, so this is still slow. So it's not enough just to do flash attention and expect that it's going to work well, that it's going to be practical with 10 million tokens. We need to do something else. But at least we are not going to explode with the memory of the GPU, right? So, the way it works is by exploiting, is by modifying the way attention is computed and exploit the fast memory of the GPU. So this has been the main enabler for this exponential increase, I would argue. but not the only thing. Okay, so another thing that was not in the original transformers paper and became mainstream is something called GQA, or grouped query attention, where before I mentioned about okay, for every ad you have a query, a key, and a value projection matrix, but in fact you don't need to have exactly the same number for everything. So in group query attention, we are sharing some keys and values for the queries in order to reduce the size of the key value cache, or KV cache, okay, which is basically what you need to store when you are computing attention progressively. So another line of work that is very interesting is linear transformers. So if we recall the attention expression, I'm skipping here the scaling by square root of t. That's not going to be important for making these points, but it looks like this, right? And so the pain comes here because this multiplication of key times q times k transposed. It's going to result in an n by n matrix. As n gets very large, n being the context size, we cannot afford to store these metrics explicitly. But what happens if you remove the softmax transformation? Okay, so this is no longer a regular transformer. People call it a linear transformer. So in that case, it becomes this. But now you can use the associative property of matrix multiplication, and you can do the multiplication of k transpose v before before multiplying by q. Okay, and now this multiplication is much cheaper because we no longer need to materialize n by n matrix. Okay, so this is a very simple trick. We can reduce the computational cost from d squared times n to dn squared. Sorry, the opposite. So from dn squared to d squared n. Okay, so it becomes linear in n. So this is related to things that are much older, like fast weight programmers by Schmidt-Huber in '92. And it's related to, yeah, so I wanted to bring this slide because it makes a very nice point that at first sight might be very surprising, which is linear transformers are RNNs. Okay, so this is the title of a paper at ICML 2020. So if I take the previous expression, so this expression here, and write it as a summation. So let's assume we are in the decoder, so you need to do causal masking. So the summation goes up to I. We cannot attend to future information. Then this boils down to this. Okay, so the new representation Zi is going to be a big summation of outer products between keys and values times the query QI. Now I can call this summation Hi. It's a matrix. Okay, and I can write exactly the same thing as a bunch of sequential updates. Right? I can write Hi as the previous Hi minus 1. So all terms of this sum except the last one, plus the new term Ki times Vi transposed. Okay? And then Zi is just multiplying Hi by Qi. Now, if you look at this now looks like a linear RNN. There is no linearity here. Everything is linear. This is a matrix, but you can flatten this matrix and turn that into a vector. And if you do that, it becomes exactly a linear RNN. Okay? So this point has been made by other literature that was trying to develop linear RNNs, like state space models, Mamba, which is a little bit more sophisticated version with gating, RWKV, gated delta nets. All these things can be regarded as linear transformers. So there is like a shared space between transformers if you linearize them, and some of these recurrent models. Okay, and in fact, most of the recent architectures that are coming out. So very recently, we had Kimi K3 released and the new Quen as well. They are all hybrids that interleave full attention layers with linear layers that are like linear transformers in various kinds. Some of them are Mamba, some are gated delta nets, and so on. Okay, so I think I'll need to wrap up. So one class of methods that this is also covered in the TIE survey, and this is work that was done in our group. I'm just going to mention it very briefly because there's going to be another talk tomorrow afternoon by Marcos Treviso, where he's going to talk in more details about these things. But the idea here is to replace softmax by a different transformation that is sparse. I think Mario mentioned sparse max in his lecture, which is basically doing this. So you can have like a broader family that includes softmax and sparse-max as particular cases. And there is this hyperparameter alpha. When alpha is 1, we have softmax. When alpha is 2, you have sparse-max. But for any alpha that is strictly greater than 1, this transformation can be sparse. And because it can be sparse, when we plug it in an attention mechanism, it means that it can ignore some tokens, right? And you can exploit that to make things more efficient. So don't worry about this expression. This is something that Marcus is going to explain in more detail. So we did that a long time ago in 2019. This was our first attempt to replace softmax attention by this alpha and max attention to get something that is adaptively sparse. But recently, only recently, starting last year, there were 2 papers at ICML, one last year, another one this year. One of my students got very excited about this. He started to write efficient implementations in Triton, and we came up with the equivalent of flash attention for these sparse attention mechanisms. So I'm going to skip this because Marcus is going to talk about this in more detail. But the main point is that this scales very well with context size, so it's a very promising avenue for future work, and it also has much better lens generalization than softmax. So we can also try to build hierarchical versions of these things, okay? So another solution that was also something done in our group is doing attention in a continuous space. So suppose that instead of representing your memory as a sequence of tokens, suppose that you represent it as a continuous signal and you parameterize it using some basis functions, okay? So this is nice because by choosing the number of basis functions, you can allocate how much computation you want to perform to represent your entire memory. And you can also put more resolution in areas of the memory that are more important and remove it to areas that are where nothing interesting happened. For example, if you are modeling video, which was the topic of this ICML paper with my student Saul, might be there. In long videos, there's parts of the video that are completely uninteresting. So maybe you don't need to waste a lot of basis functions in those regions. And there are parts of the video where lots of interesting things are happening. So maybe you need more granularity in those memories. And you can do that if you do these computations in a continuous space. Okay, so can I have 5 more minutes before the break to wrap up this part so that I can just start with LLMs right after? So there is yet another thing that I want to mention, which is what next, right? So we already saw that we are abusing transformers. There is this very nice website. How many of you have seen this, by the way? Can you raise your arm? Okay, no one. Okay, interesting. So you can go to isattentionallyouneed.com. There was a famous bet between Jonathan Frankel and Sasha Rush. I think they did this like 2 or 3 years ago. And the question was, are we still going to use transformers in 2027? Is transformers still going to be the main thing in 2027? And people could vote yes or no. Okay, so Jonathan Frankel thinks yes, we are still going to use transformers. Sasha says no. My opinion is that we are not going to be able to say yes or no because things are going to be so blended that it's going to be debatable if we are still talking about transformers or not. But officially, I think the current status is still yes. Okay, there's still some days left. So let's see what happens. But so one way to, if you want to replace transformers by something better, we should start by understanding what transformers are doing and what are the things that they do well and the things where they need to be improved. So I started the talk by talking about associative memories and making these connections with off-field networks. There is another perspective that I want to bring, which is we can think of transformers as fast in-context learners through something called kernel regression performed at test time. So let me explain what I mean with this. So I talked earlier about the KV cache, the key value cache, right? You are accumulating the keys and values for the past tokens that have been generated. And so you can think of this KV cache as your memory, right? So at time step t, your KV cache is going to contain all the keys and values up to t-1. And now let's assume that you are in time step t, so you have to generate the next token. And therefore, we have a new query, okay? So I'm going to assume for convenience that queries and keys are the same. So we are going to use the same projection matrices for queries and keys. And our goal is to, let's assume that our goal is to predict what's going to be the next value. Okay, so I have this query, which is the same thing as the key at time step t, and I want to predict vt. Okay, and so to predict vt, because vt is a vector, I can think about computing the expectation of vt condition on the new key and the KV cache, all the previous history of keys and values. And if you think about it, this is like a regression problem. So this memory is our data. Our data is inputs, outputs. Inputs are keys, outputs are values. And now you have a new input, which is KT, and you want to predict what is the output that corresponds to that input, okay, which is going to be VT. So this is a regression problem. Regression problems can be solved in many different ways, right? So there is a very nice paper by Wang et al. That describes how many different architectures, transformers, Mamba, state space models, and so on, they can all be seen as different regression solutions to this problem. So let's see what transformers do. Transformers use a method that is very famous in statistics called the Nadaraya-Watson estimator. This is a non-parametric kernel regression technique. And the idea, the way it works is you define a smoothing kernel function with some bandwidth. And to estimate the corresponding value to a key KT, we are going to look at how far is this, this new key or this query to each of the keys in our KV cache, and we are going to use those things as weights to the corresponding values in that KV cache. So you want to give more weights to values that are associated with keys that are very similar to the current key that we have now, right? So it's very common to use things like Gaussian kernels for this kind of estimation. So now if you use a Gaussian kernel with some bandwidth h, and assuming that keys are normalized, which is basically what happens if you are using RMS prop, RMS norm, then by doing the math, this is very simple math, you just replace these by the expression for the Gaussian kernel, and you're going to have a bunch of exponentials in the numerator divided by a sum of exponentials in the denominator. And so you can write the entire thing as a softmax that compares your current key or query with all the other keys and uses as a weight to associate with the values. Okay, this is exactly what softmax self-attention is doing. Okay, so you can think of softmax self-attention in transformers as doing at test time this kernel regression technique using a Gaussian kernel. Okay, I find this very insightful because you can think of what attention is doing as something that corresponds to a learning problem, but being performed at test time. So if you think about in context learning, when you use prompting and provide a few short examples and so on, transformers are learning that on the fly because they are doing something at test time that is solving a learning problem. Of course, you don't need to use a Gaussian kernel. You can use a different kernel. In fact, for those of you that are familiar with non-parametric statistics, statisticians, they like kernels with compact supports because they have some nice properties. So instead of using a Gaussian kernel like this thing in blue, they like these functions like this. And it turns out that if you replace the Gaussian kernel by these compact kernels, we can recover the sparse attention techniques that I talked about in a few slides before. Okay, so this is described in a paper that we have in archive with my student Saul, who might be seated somewhere, and my other student Nun. Okay, so this is my last slide before the break. This question has no answer yet. If there's going to be a new transformer in 2027. But we might wonder if recurrent models are coming back. When transformers were proposed, it seemed to be the death of RNNs. But in fact, many of current models, state space models, Mamba, gated AltaNets, they are recurrent. The current trend is to hybridize transformers by interleaving self-attention layers with some of these recurrent layers. I don't know at which point we will stop call these transformers because they are starting to depart a bit from transformers. Sasha Rush made a poll recently in Twitter asking if we should still call Kimi K3 a transformer or not. There's two related perspectives. We can, coming from both sides, you can think about making transformers more efficient by compressing the KV cache, compressing the memory to avoid quadratic growth. If you come from the side of recurrent neural network, or Mamba, if you want, the bottleneck is different, right? So a single vector is too little to encode all the memory. So they want to expand the state size, making the state size dynamic as more tokens appear. Your memory should increase. Maybe not increase too much because you don't want to have a quadratic bottleneck. And so these things will meet somewhere, right? Expanding the state size in current models or compressing the KV cache, will meet in the middle. In general, it's insightful to think about what are the memory properties that we want. There's a lot of recent work built upon this perspective. So memory mosaics is something that Leon Boutou talked very briefly in his talk. It's work that he did when he was still at Meta. At Google, they are developing things like Titans, Myras, and so on that are also trying to become the new transformer. There's a few other things like hierarchical memories, dynamic sparsity. I didn't talk about MOEs here because there is no time. But there is a tutorial that we have in this topic with Eduardo Ponti in NeurIPS 2024 that you might want to take a look if you're interested in learning about some of those things. Okay, so this is time for a coffee break. So let's take a break and come back in the second part to talk about LLMs.
Querem definir como é que é como é que são os óculos dela?
Maybe in English. A hair thing. Eu sei que é mais estranho. Vou não tirar muito tempo à tua, mas pode ir agora no princípio, depois no fim vai ter questão. Hello, hello. Anyone recognizes these glasses? Someone was here the first day and just left. No one knows this? Belong to anyone? Okay. A hair thing. It's useless for me, but for this? Okay, go ahead. It's yours. A bottle. Anyone gives more than 3 euros? No. 5 euros. Okay, let's go on.
Okay, so let's get back to the second part. In this second part, I'm going to talk about large language models. Now that we covered the architecture behind these models, let's go straight about the models themselves. Okay, so we saw already in Noah's lecture yesterday that this idea of predicting the next words can be very powerful because it can make very good representations emerge. And so the idea is very simple, right? You just model the conditional probability of the next token, condition on the previous tokens. Fortunately, there's lots of data for this, textual data in the web. You don't need to ask people to annotate this data. We don't need labels. We just need raw text. And the idea of using language modeling to obtain representations is something called unsupervised pre-training or self-supervised learning. So yeah, that's the basic idea. It's not the only way. So one alternative to predicting the next words is to mask words and then train the model to recover the words that have been masked. I'm going to talk a little bit about that in a bit. And of course, you can do the same thing with other modalities besides text. For example, for images, you can hide a part of the image and train a model to recover the missing part of the image. The same thing works with speech and audio signals and so on. Okay, so let's look a little bit closer to this idea of pre-training a language model and then fine-tuning afterwards. So the first step, it's what we already saw. The second step, suppose that you want to build a system for sentiment classification. For example, you have some data with movie reviews, and you want to train a model to be able to predict if a review is positive or negative, right? But you usually don't have a lot of data for this. You might have like a few thousand examples or something like that, which is much less than the amount of data that you use to pre-train your LLM. So in that case, what you do is you start by pre-training an LLM, or you use an LLM that has been pre-trained by someone, and you use it to initialize step 2, right, where you fine-tune this model on a new task, right? So this paradigm, pre-training and fine-tuning, is very powerful. It's a bit outdated already, but I'm going to explain a little bit what you can do with it and different ways where you can apply these principles. So there's three kinds of architectures that have been used for pre-training and fine-tuning: decoder only, encoder only, and encoder decoder. And I'm going to start with decoder only. Okay, so this is the language model example that I gave before. fine-tuning here means that you keep all the parameters of a language model, or we initialize with these parameters, and you just append some layer, for example, a linear layer, on top of the representation of the last symbol. Okay. And then you just need to learn the weights of this linear layer. For example, this matrix A and this bias B. And if you want to do something like a sentiment classification, for example, you can just train the model to have to minimize the loss in that task. So in fact, there's two common choices for fine-tuning. You can either freeze the pre-trained model completely and train only this linear layer, or we can also fine-tune everything, including the language model parameters. It's going to be more costly because you typically have way more parameters in the language model than in this last layer. But typically you can do a little bit better because you can gain from backpropagating gradient information through the entire network. And so pre-trained decoders are particularly convenient if you are doing a task that is related to generation. The most famous example is the family of GPT models developed by OpenAI, but these days there's many other choices. Just to give you some perspective about these GPT models, the first version was presented in 2018. It was quite successful as a technique to pre-train a decoder, not as famous as later ChatGPT became, but this was a transformer decoder with 12 layers, so pretty much the architecture that I mentioned in the first part of the talk. Train on a books corpus, which is a dataset that is now deprecated because it violates copyrights. But so this was 7,000 books, and it was very effective. Okay, so the second one became a lot more famous, GPT-2. How many of you remember GPT-2 when it was introduced? Okay, quite a few arms. So this one was a larger model trained on 40 gigabytes of internet texts. It is much stronger in language generation tasks. The total number of parameters was 1.5 billion parameters, which for today's standards doesn't look a lot. But at this time, 1.5 billion was quite a lot. Okay, so and the training task was the same as we have been talking so far, predicting the next words condition on the previous words. They did some innovations in how to decode these models by doing top K sampling, and it generated a lot of hype. So there is this very famous example that some of you might remember. So they showed examples where GPT-2 could complete stories. So it was mostly done for creative tasks like fiction machines, as in Leon Boutu's talk, where we start with a context that is written by a person. In this famous example, the context is this: in a shocking finding, scientists discover the herds of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorn spoke perfect English. And then GPT-2 completes with a plausible continuation for these stories. And one thing that was quite remarkable at the time, it sounds less impressive now, is that some of the things that are picked by the model, for example, the name of the biologist is a Spanish name, which makes sense because we are talking about the Andes Mountains. There is a mention to the University of La Paz. Everything becomes quite coherent and consistent, which was not the case in any other language model at this time. So this was a big step forwards. Later, there were more versions of these models, GPT-3 and everything that followed after ChatGPT. I'm going to come back to this family of models later. But before, I'm going to jump to the second kind of architecture, encoder-only architectures. So the idea here is that we want to leverage bidirectional contexts, not just pre-train on language modeling that provides only left to right information, but rather we want to pre-train a model by letting contextual information flow from both sides. Okay, but then we need to think about how to pre-train these models. Okay, so we cannot pre-train on standard language modeling because language modeling you need to have a causal mask. You need to have something that works left to right. So you need to come up with something different. What works for encoder-only models is to do something called masked language modeling. Okay. So the idea is very simple. So you get a sentence in your data. You randomly mask some words. The magic number is you mask 15% of the words, right? So people revisited this number later on, but that was the proposal in the first attempts. And then you train the model to recover the words that have been masked. So for this example, I went to the store, you mask the words went and store, and then you train the model, you put a loss function associated with these words, which you can think as a denoising autoencoder. Okay, so I don't know if denoising autoencoders were covered in the school, probably not, but you might have heard of them. So the idea is that you add some noise to the inputs, so you are corrupting the inputs, and you train the model to recover the information that has been corrupted. And there's many kinds of noise you can use. You can add Gaussian noise, but there is a particular kind of noise which is masking information, right? So this is what is being done in masked language modeling. You mask random words, and then you train the model to recover that information in the output. So the most famous example of an encoder-only model is BERT. How many of you remember BERT? Okay. Did you ever use BERT in your research? Okay, interesting. So this was after BERT, this was extremely influential in the field. It was probably the first convincing example of a model that could be used for many different tasks. So BERT stands for bidirectional encoder representations from transformers. It uses this 15% masking probability that I mentioned earlier. The big novelty was the ability to leverage both left and right contexts. And as a byproduct, they learn contextualized word representation. So what the work that built on top of BERT did was to take these representations out, fine-tune the model for new tasks, and this was a very effective strategy. Okay, the BERT paper also achieved state-of-the-art results in many different NLP tasks, which today again sounds not super impressive because current models are very versatile. But at this time, you didn't have any model that can be used to achieve state-of-the-art numbers for so many different tasks. So here's some details about BERT. So they released two models with the paper, one with 12 layers, another one with 24 layers, trained also on books corpus, but also on the English Wikipedia. At the time, this was done at Google. They used TPUs, and it will be impractical for someone to do this in an academic lab on a GPU. But the point is that the pre-training only needs to be done once, and then you can take the weights of the model and fine-tune many times for wherever task you like, right? So the paradigm was pre-train once, fine-tune many times. And it became very influential, right? As I was saying, it achieved state-of-the-art results for many NLP tasks. There's other variants that followed. One of the most famous was Roberta, which is basically what Meta did to redo BERT, simplifying a little bit what BERT was doing. They also released a multilingual version called XLM Roberta. Our group also did some work recently on these, revisiting these encoder-only models. So if you're interested in a model that has good support for European languages, you should check out AeroBERT. This was a project led by the University of Paris-Saclay, but with some students from our group also contributing. But so overall, to summarize this part, encoder-only models kind of fell a bit out of fashion because the decoder-only models ended up prevailing, but they are still relevant in several scenarios. For example, they are quite relevant as embedding models. So if you have a RAG, retrieval augmented generation system where you combine information that you can index with generation, then you need to produce embeddings for the text that you are indexing, and encoder-only models are a good choice for that because they can typically be much smaller than decoder language models. You can also use encoder-only models to train as reward models because in reward models, you are trying to produce a score for a given answer. You don't need to generate, right? And finally, recently there is a lot of interesting work being done with the mask diffusion language models, which are non-autoregressive models. They don't decode left to right. And the architecture of these models follow very closely what is typically done with masked language modeling in encoder-only models. So we can also take an encoder-only model and use it in a diffusion setup. Okay, so and finally we have encoder-decoder models. They were introduced to try to get the best of both worlds. So the idea here is that you keep both components, the encoder and the decoder. So you still benefit from bidirectional context, but you can also train the model to generate. And the typical auxiliary task that is used in these models, where T5 text-to-text transfer transformer is the most famous example, is span corruption. So the idea here is similar to BERT, except that instead of masking just individual words, you mask entire spans. For example, here, if the original sentence is this one, thank you for inviting me to your party last week, you can just mask the span for inviting. So you just replace these two words by a placeholder symbol, X in this case, and you can mask lasts. And then the model is trained to produce the text that corresponds to each of the placeholders. So now it needs to generate. So it needs the decoder part of the model. So it should output X, and then what should be in that placeholder. Then it outputs Y, and what should be in that placeholder, and then it outputs some stop symbol. Okay. So T5 was interesting because they showed that the model could be fine-tuned to answer a wide range of questions. So basically, they were trying to map every NLP problem to a question-answering problem, and they also realized that the model would be very good at remembering factual information, right? Okay, so these are the most famous examples of this pre-training and fine-tuning paradigm. But this has several limitations, okay? So a big limitation is that if you want to have a model that performs a very large number of tasks, if you are not interested only on, let's say, sentiment classification, but you want to have a model that can perform 1,000 tasks, then this becomes quite expensive, right? You don't want to fine-tune your model 1,000 times, one for each task. It's going to be quite costly. And you are going to end up with copies, with 1,000 copies of the model, which is going to consume a lot of memory. So can we make this more efficient? And a lot of research followed on parameter efficient fine-tuning using things like adapters. So the idea is, instead of fine-tuning the full model, we can fine-tune only, or we can train only a small set of task-specific parameters called adapters, and includes the other parameters of the model without touching them. And so this comes with many advantages, right? Now you have much fewer parameters to fine-tune. We can share the big pre-trained models across multiple tasks. So again, if you have 1,000 tasks, you need to train 1,000 small adapters, but they are really, really small. And all of them can share the pre-trained backbone, right? Which is way more efficient. And you can also combine these adapters in combinatorial ways. For example, you can have one adapter for the task and one adapter for the language, so that you can perform any task in a range of different languages. So adapters look like this. So basically what we do is you introduce some extra boxes in your transformer. In the initial version, this was interleaved with the other transformer layers. So for example, after the feed-forward layer, you would introduce an adapter, and the adapter is a small model that contains some feed-forward down projects, some nonlinearity, and then some feed-forward up project that puts things back to the same dimension size. And it will be a cheap way of adapting the model to specific tasks. Okay, so another strategy that became a lot more popular is LoRa, or low rank adaptation, which is the same idea, but now they do this. They place the adapter in parallel instead of sequentially, and they get rid of the nonlinearity. So in this case, you have the pre-trained weights that you don't touch, and you just you just learn a perturbation of those weights, this delta W here, by considering a simple two linear layers that are basically projecting things to a lower dimensional, and then putting things back on the original dimension, which you can see as a low rank modification of the original weights, right? Because B times A is going to have rank R. Okay, the rank corresponds to the dimensionality of this dimension here. So the rest is the same. You just freeze the original weights. You just learn A and B, and that's the only thing you have to learn, right? And there's lots of software support for LoRa. So it became. Oh, I mean, if you used LoRa at some point, okay. So you know what this means, right? So if you are on a academic budget and you don't have a lot of GPUs, most of the time, if you want to do any sort of fine tuning, you need to resort to LoRa or something similar to be practical. So they showed that LoRa exhibits better scalability and sometimes performance than full fine tuning and other methods. I think in general, full fine tuning is still a little bit better, but LoRa can get pretty close. So here this is showing how much the accuracy for your task depends on the number of trainable parameters. And the main point is that with LoRa, which is these pink triangles here, you can kind of keep the same accuracy as using the full model, but with the orders of magnitude fewer trainable parameters. Okay, so this ends this pre-training and fine-tuning era that where BERT was a good representative. Now I'm going to move on to prompting and in-context learning, which defines what the GPT-3 started. And this building on the previous point, adapters are nice because now you need to fine-tune less. But what if you want to solve a completely new task for which we don't even have any training examples, or you just have like a handful of examples? So you cannot really fine-tune a model, not even with LoRa, to adapt to your tasks. What if you want to make the model learn those tasks on the fly? Okay, so I briefly touched the topic of in-context learning when I was talking about kernel regression, test time kernel regression in transformers. This is the kind of thing that you want to do with this model. So this is called few-shot learning for only a few examples. And there was a remarkable progress with the GPT-3 as a model that showed that this was possible by doing prompting. Okay. All right, so let's look at the GPT-3. The first thing to notice about GPT-3 is that it was a huge model for the time standards. It's still very big even for today's standards. 175 billion parameters, trained on 500 billion words. It took a lot of flops to train. Someone did the math, and on a standard GPU at the time, it would cost $4.6 million, and it will require 355 years to train this. But this model also introduced prompting as an alternative to fine tuning, and it demonstrates that these models are able to demonstrate few-shot learning capabilities. So this is like to put things into perspective, right? So before GPT-3, the biggest models were around 17 billion parameters, 9.4 billion, and then there was a huge jump with the 175 billion parameter model. So scaling up LLMs is a huge engineering effort. In order to do this, not just for GPT-3, but even for any scaling that you do, you should avoid wasting too much compute, right? So the way to do this is by doing careful scaling loss, trying to predict what's going to be the performance as you scale up the number of parameters of a model without actually training that model. So you can train smaller models, evaluate those models on benchmarks, and then try to anticipate what's going to happen if you keep increasing the model that way. And in GPT-3, they did a lot of scaling studies in order to anticipate what would happen. And if you do that, and if you start plotting those things as they did, they start noticing a lot of regularities. For example, they noticed that first models decrease the validation loss significantly, and then they start either plateauing or decreasing a little bit slower. But if you look at the slopes of, if you look at the frontier of those losses, things seem to align as a straight line, right? So you can actually try to solve a linear regression problem to try to anticipate what's going to be your validation loss as you increase the size of the model. So there's many ways of doing that, and sometimes things can get a bit misleading. For example, initial work suggested that you should, if you want to maximize your performance and you have a compute budget, the optimal thing to do is to train not until you have the best possible validation loss, but to train a bigger model and then not training it to optimality because it uses the compute budget more efficiently than using a smaller model and training to optimality, right? You know, this was a bit questionable, and at this stage, people were also neglecting the inference costs that are necessary. Once you are done in your model, you have to deploy it. That is going to consume resources. If models are very big, then you're going to pay a price at test time. But so a very famous paper is this one that introduced the chinchilla loss that tries to come up with a formula that tells you, okay, for a model of this size, how many training tokens are necessary to train this model. And the conclusion here that they got is that GPT-3 was very undertrained. So GPT-3 was trained on only 300 billion tokens. To put things in perspective, Llama, that was a little bit later, was trained, it's a much smaller model, 7B and 13B, the first version of Llama. And this was trained on 1 trillion tokens, which is 3 times more than GPT-3, even though the model is much smaller. And if you look at today's models, for example, models from the Qwen 3 family, they were trained on 36 trillion tokens, right? So the current tendency is to overtrain these models, to train on a lot of tokens because they keep improving. And people are not following these chinchilla laws anymore. But Chinchilla noticed that the GPT-3 was already undertraining their models. Okay, so let's talk about this paradigm of prompting and in context learning that followed the idea of pre-training and fine-tuning that I mentioned earlier. So as I mentioned before, pre-trained language models, they acquire a lot of factual knowledge, and this suggests that we can prompt them on the fly to solve new tasks. Okay, so this is a plot taken from a diagram taken from the GPT-3 paper, where they showed two kinds of learning. The traditional fine-tuning is what we have in the right, where for every time we have a new example or a new batch of examples, you do a gradient update to the weights of your model. Right? This is how you typically do fine-tuning. In GPT-3, they show that they could do something a bit different, right? So they provide examples as part of the context. For example, here, if you want to have the model translate the word cheese from English to French, you can ask directly the model to translate from English to French because maybe the model has seen some translation data at pre-training, and just by being given this instruction, it knows exactly what it should do. For tasks that are more complicated, sometimes you have to provide one example. This is a one-shot example, right? So here you provide the translation of sea otter into French, and then you ask the translation of cheese. For tasks that are even more complicated, you might benefit from introducing multiple examples. This is few-shot learning, but typically few examples, right? Something that fits in the context of a transformer. And you can see that here there is no gradient updates, right? The weights of the model are not changed. Everything is being done at test time. So this is leveraging this test time kernel regression that I mentioned in the first part. Okay, and this was the first paper that showed that it was possible to do in context learning very effectively. So they had several interesting examples in their paper where they come up with the made up tasks, for example, making up names for things. The parts in gray are examples that are written by humans. In this case, it's a one-shot example. You know, these made up words where you invent a word and you ask the model to generate a sentence, including that word. The second time we come up with a new word and the model generates a plausible sentence with that word. So the model knows exactly what it should do. Okay. So other examples include grammar correction. I guess many of you saw this already when you interact with today's models. Auto-completing codes. You know, now we have Claude Code, but the first signs that it was possible to auto-complete codes started from around 2021. But one thing that is important to make is that language modeling is not the same thing as assisting users, right? This point was already made by Leon Boutu's talk. I think he showed exactly the same example, or if it was not the same example, it was a very similar one. if you take a GPT-3, as I just described, trained on next word prediction, and you prompt it with this, explain the moon landing to a 6-year-old in a few sentences, this is what GPT-3 is going to generate. It's not going to generate an answer to your question. It's going to generate, plausible ways to, continue from these prompts, which might include further questions as opposed to an answer. Okay. So in order to have something that can work as an assistant, you have to tune the models to follow instructions and providing answers. So you need to do something like instruction tuning. Okay, so for this particular example, you want something like this. Okay, this is a human answer to this question, a short explanation to the question that is being given. Okay, so how do you do that? That brings us to the next era, the ChatGPT era, the era of post-training and preference optimization. So the first thing that people tried was to fine-tune on instruction data. So they asked humans to come up with answers to a lot of questions, multiple tasks, a diverse set of tasks, splitting between tasks that you provide to models when you are fine-tuning them and tasks that are held out only for evaluation purposes, right? Because you want to test how well models can generalize to unseen tasks. And the idea is to provide during fine-tuning as diverse tasks as you can, so that the model learns how to play with the format of these tasks more than anything else. So one successful paper that shows how to do this is FLAN T5. They curated a data set with those fine-tuning tasks and with some LLM tasks, and then they just did the supervised fine-tuning. With a specific chat templates to mimic these, assistant interaction. But the problem is that this is still expensive, right? So you need to have human answers to a lot of questions. So something that some people thought, independently in several groups, was to generate synthetic instruction data. So instead of asking humans to provide answers, maybe you can ask a very strong LLM to generate instruction data for you, right? So this was done, for example, at Stanford with the alpaca model, which was basically a llama model, which was released as an open weights model, and they used ChatGPT to generate instructions, and then they trained they fine-tuned their llama model on this ChatGPT data, and by doing that, the model behaved like an assistant. The same thing was done in other places, like in Berkeley, they had Vicuna, Tulu in AI2. Our group also created a dataset for this, again, with a focus on European languages called Euroblocks. But yeah, that's the basic idea. There was one hypothesis coming from this paper, Lima, less is more for alignments, which is pre-trained models, pre-trained LLMs, they already have all the knowledge, but they don't know how to express it very well. So the value of instruction tuning is more to teach them how to express their knowledge, how to elicit, how they should behave as assistants. And so this is a very optimistic hypothesis, but it kind of, I would argue it holds, at least partially. And it made it possible to have an instruction tuning phase with very few instructions. So Alpaca was like around 1,000 different instructions, and that was sufficient for the model to generalize to many unseen tasks. But of course, there's still limitations on these approaches. I already mentioned that it's expensive to collect human instructions. You can alleviate that by using synthetic instruction tuning data, but there's other problems. For example, suppose that you want to do open-ended creative generation. For example, the explaining moon landing to a kid, something like that, or generating a story like the unicorn story that I mentioned before. For those examples, there is no single correct answer, right? There's many plausible, many good ways of generating tests. And if you just provide some answers collected by a person or synthetically, you are going to provide only feedback to the model about a single answer, and you are not valuing other plausible ways of continuing that story. So we are not letting the model explore how it should go about completing the story. Related to this problem, if you do supervised fine tuning with a cross entropy loss, all you are doing is to maximize the probability of the next token, right? So you are penalizing all token level mistakes equally, but of course there are errors that are more important than others. For example, if the model fails on predicting a comma where there should be a comma, it's probably going to be less important than giving you an incorrect number for a math problem. And finally, there is yet another problem, which is even with instruction tuning, there is a mismatch between the objective function that we use in SFT, which is minimizing perplexity or cross entropy, and the objective of satisfying human preferences. And so at this point, people start thinking about, okay, how can we explicitly try to satisfy human preferences? If you want to have an assistant that interacts with people, that's what we should think about. And so an effective recipe goes like this. So instead of using only one ground truth answer, we start by presenting a question to a model and sampling several possible answers from this model. Let's call them Y1, Y2, and so on. And then you ask humans to express their preferences. So humans would say, I like Y2 better than Y1. Then we can use this preference information to train a reward model. And our goal is that the reward model should assign bigger rewards to things that humans prefer more, right? Now, once we have a reward model, what we can do is to train the LLM to explore and to maximize this reward, right? This is what reinforcement learning does. And there's going to be a lecture in the afternoon that Zita is going to teach, where she's going to go in a lot more details about reinforcement learning, okay? Right, so if you want to look a little bit more at what we can do with human preferences, take a look at this survey from my former student, Patrick Fernandes, that does a good job at putting everything together. I'm going to elaborate a little bit more on this reward model. So typically, human judgments are noisy and miscalibrated. So those of you who conducted, user studies for evaluation might have noticed that humans tend to be pretty inconsistent. If you ask the same person the same question in 2 different times, you might get different answers. So if you give different possibilities and ask for the preferences, maybe in some cases they give a very high score to some answer and a low score the next day. One way to try to not work with absolute scores is to ask people for pairwise preferences. It's still not bulletproof, but it tends to be a little bit more stable. So this means that you present 2 options, and then you ask people which of these 2 options they prefer, or if they don't prefer any, okay? So if we do this at scale, and OpenAI did this at a huge scale, paying very little to the human annotators, by the way. So if you do this at scale, you are going to obtain a bunch of triples, where we have your original question X, and then you have a winning answer in green here, YW, and the losing answer, YL, right? And so what you want to do is to train the reward model to be compliant with these preferences. So we want the reward model to give a higher reward to YW than it gives to YL, right? And so there is a very interesting, a very good statistical model to solve this kind of ranking problems called the Bradley-Terry model. It does exactly this. The way it works is, you train your, so this phi here is the parameters of your reward model, okay? That's what you want to train. Your loss function looks like this. So it's going to be a sigmoid of the difference of the 2 rewards, the winning answer minus the losing answer. And then you minimize the negative log likelihoods induced by this sigmoid transformation. And so the intuition here is that the YW should score higher according to your reward model than YL. So putting all together, we now have everything that we need. Okay, so we have the pre-trained LLM, and we can assume that it's already been instruction tuned with the SFT. Okay, with the condition on some human answers, for example. now you also have a new reward model that optimizes the Bradley-Terry loss that I showed in the previous slides. And this model is going to produce scalar rewards for the LLM. And we can assume that we have a method, a reinforcement learning method, that optimizes the LLM parameters towards these rewards. So if you have that, then we can do what's called reinforcement learning with human feedback. So we typically initialize your model for the next step as a copy of the pre-trained model. By the way, I didn't mention that in the slide, but the reward model is typically also initialized from the pre-trained model, except that you change the heads of this model to do to output a continuous score as opposed to generating. And then we optimize the rewards with reinforcement learning. So the most common approach in these early times, and that's what OpenAI proposed, was to use something called PPO, proximal policy optimization, where you basically minimize this objective function, where you want to maximize, actually. So you want to maximize the rewards, but you also have a regularization. You don't want the model to deviate too much from the pre-trained model. The reason for that is that if you don't have this term on the right, models tend to drift very quickly. So they start chasing the rewards. The reward is going to be imperfect because it's a model that you train on your preference data, but it can start giving weird rewards for weird things. And if you allow the model to deviate too much from the pre-trained model, you might end up with something very suboptimal. So you can think of this as a regularizer, okay? And you can think of this term here as a KL divergence. I don't know if, Mari, did you talk about KL divergence? Okay, so if you don't know what KL divergence is, don't worry. Yeah, so the expectation of this term is the Kullback-Leibler divergence. So it measures how much this probability distribution is deviating from this one, okay? Okay, so this is the full picture that comes from one of the OpenAI papers, right? Step one is collecting demonstration data and doing SFT. Second stage, collecting human preferences and use them to train a reward model with the Bradley-Terry loss. The third step is to optimize a policy against that reward model with an algorithm like PPO. And so this was what the InstructGPT paper did in 2022. They scaled up RLHF to tens of thousands of tasks with a massive human feedback. And by doing that, they managed to provide a more satisfactory answer to this prompt, right? So no longer the output of GPT-3, but now actually some text that takes into account people's preferences. And ChatGPT was just a continuation of that, right? So it's basically using the same method, but now for a dialogue agent, where humans played both sides during annotation. They played the user side and they also played the AI assistant side. And they did several RLHF rounds of this, okay? So preferences go a long way, right? So you can train model to satisfy preferences, for example, in terms of the format in which they should write answers. If your audience is a Generation Z audience, which might be the case for this school, you might ask the model to generate an answer with lots of emojis, which I think they already generate by default, at least maybe not emojis, but very specific formatting. And this will be the result, okay? But RLHF has also limitations, right? I already touched one of them. If you don't regularize PPO, to not deviating too much from the pre-trained model, it's going to start chasing the reward too much. So reward hacking is a big issue. Chatbots are rewarded to produce responses that seem authoritative and helpful, even if they are not true, because I think Leon made this point in his talk. Humans, it takes a time for us to understand if the answer is correct or not. So when a human is generating human preference data, it might prefer an answer that is wrong, right? And so as a result, these models often hallucinate, and they hallucinate in very convincing ways, right? Which is even worse. And so they had these plots in the InstructGPT paper where they show that if you yes, sometimes the DRM prediction goes in a different direction than the actual human preference. There's many variants and extensions of this. I think Zita is going to, I don't know if Zita is here, I don't think she is, but she's going to talk more about these topics in the afternoon, so I'm not going to get into a lot of details, but you can replace the human feedback by AI feedback. That's what Anthropic does with their constitutional AI. They have a bunch of constitutional principles that are used to guide the feedback. You can also bypass the needs for a reward model by doing direct preference optimization. If you are on an academic budget, this is probably what you are doing because it's much cheaper to do DPO than to do reinforcement learning. The way it works is instead of learning a reward model and then optimizing that reward, you directly tune your LLM to obtain a good policy taking into account the human preferences. And mathematically, you can show that you can skip these two steps and do everything in one step. I think in practice, doing it with RL is still a little bit better. So, but you can already go very far with DPO. And then you have other things like group polarized policy optimization, GRPO, DAPO, and so on and so forth. Okay, this is a very active area of research. Okay, so what happened after ChatGPT? So I remember when ChatGPT was released in November 2022, everyone was very surprised. So no one, including people at OpenAI, expected the massive adoption that followed. But a part of it was very depressing because they were serving a closed model, and the model was so good that many researchers starting questioning, should I change my career, right? Is it still worth doing something in this space? And the fact that everything was closed, makes it harder for anyone to catch up. But so there was some good news in early 2023 when Meta released Llama as an open weight model, because an entire open ecosystem emerged after that. So people started to build things on top of Llama that were worse than ChatGPT, but starting to catch up. And this plot is very outdated. If you look at today's open weight models, it's huge, right? There's tons of projects developing these models. So this is a quick summary of what happened in the 3 years that followed. There's several other closed models that have been released. Now we are already in the GPT-5 generation. There's also Gemini, Claude, Cohere, and so on. There's many more open weight models. That makes me happy that we still have open models around. Llama, Mistral. Llama is now becoming closed again, but Mistral, Gemma, Quen, DeepSeek. Last week there was the Kimi K3 model that is very powerful. Longcat, Mimo from Xiaomi. A lot of work in Chinese labs developing these models. There's also models that are fully open. By fully open, I mean you don't just release the weights openly, but you also release the data that you use to train the models. You write technical reports explaining all the training procedure, which I think is very, very important. And this has been done in many places, including in our lab with RLLM. Many of the recent models do reasoning, which I'm going to talk about in the next part. Many of the recent models are not just producing or consuming text, but they are multimodal or omni. They support language, vision, speech, and so on. And several of these models have agentic capabilities. So here's a shameless plug about RLM for those of you who never heard of it. So this is work that started from a European project, a collaboration between different universities in Europe. We are still actively working in this project, extending it in many ways. So far, we released models in 4 different sizes, all of them fully open. So not just the weights, but also the data, technical reports that describe what they are doing, code, and so on. The last version was released in December 2025. It was a 22 billion parameter model. These models support all the official European Union languages, plus some additional languages. And they consume a lot of resources for training. It's around 1.7 million GPU hours. They were trained in European supercomputers, part of the EuroHPC network, which is the network of high-performance computing. But I think to me the most important thing is the number of people that were trained in learning how to train these models. because we train like a generation of people that know how to produce these models that hopefully will make Europe less dependent on these technologies from everybody else.
I thought you were going to say that the most important thing is that there are two LXMLS t-shirts.
Oh, okay, that's a nice finding. Okay, including me, right? Okay, interesting. Me and Mark, yeah, and interestingly, so this is me and the speaker that is going to give the talk tomorrow. It was not on purpose, but a good catch by Mario. Oh, right. So I have this other slide that shows that RLM, does fairly well in benchmarks, especially in machine translation benchmarks, which are the last three. So this comparison is against other fully open models, including Apertus and Olmo. But if you look at, if you include open weight models in this comparison, these open source models, the fully open models, are still behind, right? There's still a considerable gap in these, 5 first benchmarks compared to Quen, Gemma, and so on, except for machine translation. So if you are, if you work on machine translation or something related to this topic, consider using RLM because it actually performs quite well translating across these different EU languages. Okay, so now I'm going to switch to the DeepSeek R1 era. Maybe I can make a quick stop here to see if there are any questions. Yeah.
So I have a questions about adapters. So you mentioned that you can have different adapters for different tasks, if I recall correctly, and different adapters for different languages. So are they like fully compositional, so you can just like swap them? So like basically, how is it possible so they are not dependent on each other?
Yeah, so you can combine adapters combinatorially. So one of the, I think I didn't have that slide, but the same group that developed the initial adapters before LoRa, they also did experiments with task adapters and language adapters. And they consider, like, let's say 10 tasks and 20 languages, right? And they don't need to consider all combinations when they are fine-tuning, and the model still generalizes pretty well. So because different parts of the network are modeling the task and the language. I think it's not going to be as optimal as it will be if you train the two things together, but it's common that you don't have data at the same time for every task and every language. Let's say you want to do something with Portuguese for a task like a sentiment classification. Maybe you don't have data in sentiment classification for Portuguese. Maybe you have for other tasks. So if you have different parts of the model focusing on the language and the task, you can actually do something zero shots this way.
That's cool. Thanks.
Any more questions?
Hi, I have a question about the Euro LLM because I found like interesting. Did you expect to have the such performance for for machine translation, or was something that only like happens? So I mean, like more or less in the direction that how was for the process of the LLM about the data quality, like filtering and so on? Like, do you think that might be because of that this model worked better in machine translation than in another task?
Yeah, very good question. So in the RLM projects, because we were limited in the compute that we could use, we didn't do a lot of innovation in the architecture itself because that will consume too many hours to validate these changes. But we used a lot of, we focused a lot on having a good recipe for curating the training data, both for pre-training and mid-training and post-training as well. And so I think the reason why the model became good at translation comes from two things. One is during pre-training, in the end of pre-training, in the mid-training stage, we included a lot of parallel data. More than what was common when we started. For example, other models that were developed more or less when we started, they didn't seem to use a lot of parallel data in the pre-training stage, and we saw that helped. And then in the post-training data, we also included several instructions that are translation instructions. And so the model became particularly good at those things. And then, of course, the fact that in the 24 languages of the EU, some of these languages are very low resource, like Maltese, Gaelic, and so on. And the existing models perform very poorly on those languages. So the fact that we invested in creating resources, using those languages also helped getting good performance.
Hi. So you you mentioned how people aren't really following the chinchilla laws, that they're feeding even more data than the chinchilla laws predict. My question was if there's been any work to correct the chinchilla laws, or if that's just not that an important question anymore.
Yeah, there's a lot of work that is developing scaling ways in different perspectives. The problem with the chinchilla law is that the law is correct for the question that they were asking, but people are also asking other questions. In chinchilla laws, you don't care about the computational effort that goes into deploying the model, right? If you start, if you have like constraints, like I can only deploy a 9B model, then the question changes completely. It's like, okay, how much data do I need to have the best possible 9B model, right? And that is going to be a very different number than what the chinchilla law prescribes, because the chinchilla law is going to tell you, okay, if you have this training compute budgets, instead of training a 9B model with 4 trillion tokens, you should train an 80B model in less tokens. But at the end of the day, then what are you going to do with the 80B model? You have to deploy it, but it's not going to be easy to do that. So that's what explains why many labs started to overtrain their models, starting with Llama and following on the others.
Thank you.
On the same subject of overtraining, is this mostly seen only during pre and mid training, or do people also do it during like SFT or instruction following?
The scaling loss?
Like, do people also overtrain their models during SFT?
I think people don't see it as overtraining. Like the general rule of thumb is that initially, so things might have changed a little bit over time. So with Alpaca, for example, they had 1,000 instructions, so it was very little. And because of the Lima paper that I mentioned, there was this idea that you don't need a lot of instructions because you just need to, teach the model to follow instructions. The knowledge is already there. But I would say things have shifted a little bit, and things start to be a little bit blended. So some labs are doing a lot more work during pre-training than just next word prediction. For example, starting to use RL earlier. The mid-training is getting more complex because you also do long context adaptation during mid-training. So things are a little bit. I don't think there is any rigorous study that I know about understanding what should be scaling laws for these other stages. Maybe they do that internally in some of these labs, but things get a little bit more complicated if you ask more complex questions. Yeah.
Thank you.
Okay, so I think I'm going to continue. All right, so let's enter the DeepSeek R1 era reasoning. So something that people realized is that if you ask a complex question to a model, for example, this mathematical problem, using the methods that I mentioned so far, in this case, this is a one-shot example, right? So you have a question, you provide the answer directly, and then you ask another question. And so the model is tempted to come up with an answer, but not doing enough work to achieve that answer. So in this case, it gives you the incorrect answer, 27. Okay. So this paper by Jason Y and others in 2022 realized that if you do chain of thought prompting, so if instead of in this one-shot example, you provide an answer that describes all the reasoning that goes to obtain the answer 11, so if you include this part in blue, then the model is going to do the same to answer this new question, right? And performance improves substantially. So this started to make people pay more attention to the reasoning part of these models. This is called chain of thought prompting. Later, people also did this with zero-shot chain of thought prompting, where you don't have this one-shot example anymore. Instead, you prefix the answer with an expression like this. Let's think step by step. Okay. And because of this prefix, the model is going to be encouraged to think, explicitly in several steps. This triggers the model to switch to reasoning mode if you want. Of course, these things can be very brittle, right? So why are we writing like things step by step instead of using a different expression? This paper tried different things. They also tried things that are misleading on purpose to try to understand better. If instead of let's sing step by step, you write something like this, the answer is after the proof, there is a big difference in the final accuracy, right? This is the dark part of LLMs and prompting, right? So things can vary substantially if you change the prompt a little bit. Of course, if you write something misleading, don't think, just feel, whatever, the accuracy is quite low, right? So the baseline here, by the way, is 0 shots. This is where you don't use any prefix, 17.7. But the impressive thing is that by prefixing the answer with let's think step by step, we go from 17 to 78. It's a huge jump, right? So at this point, at this point in time, some of the frontier labs are already feeling the pain of having to train models that are bigger and bigger every time. So in this plot, I'm showing in log scale from 2018 to 2023, there is an exponential increase in the number of parameters. So for example, Palm, I think it's almost 500 billion parameters. And training time scaling is just too expensive, right? It consumes too many resources. There's lots of engineering headaches that come with it. So people start thinking about, okay, maybe we should instead start thinking about scaling at test time, not at training time. So instead of producing larger models that are more capable, let's instead make models produce more tokens, doing more computational work at test time before providing the final answer. And this trend started with the OpenAI 01, 03, and so on, and then was followed up by DeepSeek R1 and many other labs. Like today's models, they all do reasoning. But so before getting into details, let me start by asking this question. So what can we do? Let's suppose that you have an LLM that is good quality and you have a reward model. What can we do with that? We already saw some examples, right? We saw that we can do RLHF. We can take the reward model, do reinforcement learning, and this is going to encourage the model to maximize the rewards, and they are going to improve the LLM as a consequence. But this is being done at fine-tuning time. It's still training time, right? The other thing we can do, I didn't talk much about that, is to do DPO. Like in this case, we avoid doing the RL. You don't do reinforcement learning. But we also spend more resources at training time. But there is something else that we can do. Can someone point what, a very simple thing that we can do if you have these two ingredients? Prompt optimization. You can also do prompt optimization, but I was expecting something that uses the reward model in a clever way. What ones? Iterative refinements. Yes. So in this case, you generate an answer, then you ask a reward, then you regenerate. Okay. Can you do something that works in parallel and not sequentially?
Sampling.
Sorry? Sampling? Yes. So you can do sampling, and what do you do next? How do you use the reward model? You use the reward model to rank, to provide a score to each sample, right? So this is basically what you said, right? You can generate many samples and then use the reward model to pick the best at test time. So this can be done completely at test time, right? It doesn't require changing anything in the training. So this option is called re-ranking or best of n. It's better known as best of n in the LLM literature, but people were doing something similar in machine translation, and they called it re-ranking. And it's a very simple way of training time by test time computes. Now we don't generate just a single sample, you generate many, and you use your reward model at test time, but you don't need to put more resources in training time. We are trading off training time by test time. So yeah, this is the very simple idea, right? You sample n answers from the LLM. You might need to increase the temperature in doing that because you want these answers to be diverse. If temperature is too small, if it's near 0, you're always going to get the same answer. So getting n times the same answer is not going to be helpful. But if you increase temperature a little bit, they're still going to be good quality and diverse. And then you can use the reward model to pick the best according to the reward that has been estimated. This works very well in practice. It was widely used even before LLMs. For example, in machine translation, our group has some work in machine translation where we use exactly this technique. We didn't call it best of n at the time. There's also more sophisticated variants that instead of ranking each example individually, they require pairwise comparisons. For example, looking at two different answers and provide some comparison which one is better, or looking at which of them is more consistent with the entire set. So in machine translation, there is this technique called minimum-based risk decoding that builds on this idea of pairwise comparisons. And I like to think of this from a communication theoretic angle, which, when you generate multiple samples, you are basically adding redundancy to the problem, right? So for those of you that have taken a course in information theory or coding theory, you might have heard about repetition codes, where if you want to transmit a message from a sender to receiver, and there is noise in the channel, like the noisy channel model, one way to increase accuracy in this communication is by sending the same message multiple times. And then the receiver can do some kind of majority voting to decode the message. And this reduces error considerably. So I would say that with best of n, we are doing something along the same spirit, not exactly the same, because we are not doing communication per se. But we have one paper where we build a little bit more on this idea with my former student, António Farinhas, where we actually make this analogy, right? So you can think of sampling as you have a sender that is generating several answers. In this model, we conceptualize it as all these answers are correct, but then there is corruption in the channels. Some of them become wrong. And then the receiver, the job of the receiver is to take these possibilities and to pick the best. This is what the re-ranker is doing, right? This is where you use the reward model to try to pick one out of this n, okay? And of course, all these components are going to be imperfect, right? So your generator is not perfect. Some of these answers might be wrong. This has to do with the noise in the channel. And your re-ranker is also not perfect. Sometimes it's not going to pick the best answer. But you show in this paper that under some assumptions, even in the situation where these systems are imperfect, you can still guarantee to decrease error asymptotically. Okay, and with this we could produce some re-ranking laws. So this is kind of same spirit as scaling laws, but instead of being for training time scaling, is for test time scaling. For all, depending on how many samples you produce, how is the error going down? And for many tasks, code generation, machine translation, also mathematical reasoning, common sense reasoning, we observed a good match between our theoretical curves and the reality. Anyway, so these techniques are nice. They still have important limitations. So the main limitation is that if you are working on a very difficult problem, let's say, for example, last week there was this proof of the Jacobian's conjecture, right? So if you try to solve this problem with best of n, you're going to fail completely, right? Because you need too many samples until you find one that is correct. And you also need the re-ranker that finds this, right? So this works in tasks that are not too complicated. If the task is too hard, then you need a very large number of hypotheses, you need a very good re-ranker, and this is going to fail. There are more sophisticated techniques. Refinement, iterative refinement could be one example, but others that also do some kind of tree exploration, like Monte Carlo tree search, sequential reasoning, which is what I'm going to talk about next, that are more effective than best of n. But best of n is a very good baseline. That works surprisingly well in many tasks. So this brings me to DeepSeek R1. How many of you remember the release of DeepSeek R1? Okay, so you might remember that when DeepSeek R1 was released, there was a big disruption in the stock markets with NVIDIA stock and other big company stock going down substantially. So this model was produced by DeepSeek in China. It was released as an open weight model, but a very capable one, right? So at this point, no one was expecting a model that could do reasoning to be deployed with such a good quality. And this paper did a lot of interesting innovations. They proposed a new RL algorithm that was better than PPO, called GRPO. They introduced the concept of verifiable rewards. They also did RL without SFT. This was a very important aspect. So I'm going to comment on several things on DeepSeek R1. This is the full pipeline. It's a little bit complicated, but they started from a base model that is already quite strong. So you cannot go very far if your base model is not strong. This is lesson number one. And then instead of doing SFT and RL afterwards, they started straight with RL. Okay, so they want to have the model explore. I'm going to explain how the RL is done in a bit. Okay, so after this RL stage, they obtained something called the R10 model. And then they're going to sample some answers from by using DeepSeek R10. They are going to filter it and curating it. And this is going to become training data for the second stage, which is now going to be SFT, using a mix of reasoning data and data that comes from R10 outputs. And this is going to produce a new model. They do RL again, and they do something else afterwards. Okay, so let's talk about the RL stage. So they came up with a format for the answers that looks like this. It's quite simple. So when the model is thinking, you enclose this information with the think brackets, and then when the model produces the final answer, you use answer tags for this answer. And because of these answer tags, it becomes easy to identify where the final answer should be, right? And if you are working on question answering where the answers are they are mathematical questions or something that you can look at an answer and identify easily if it's correct or not, then we can use you can have verifiable rewards. So the model gets a reward if the answer is correct, and it doesn't get a reward or gets a negative reward if the answer is wrong. Okay, you can also do this with code by executing the program that the model generates, right? You can get a binary reward by doing that. In addition to the accuracy rewards, they also have a format reward to ensure that the model learns to use the thinking tags and answer tags. Okay. So their idea of doing RL before SFT was to encourage the model to explore more, because SFT is like imitation learning. You are providing examples that are either generated by another model or by a person, and then you are training the model to imitate that answer, right? But the model is not going to explore, right? It's just going to follow the teacher directly. So if you do RL, we are actually forcing the model to explore. It's going to fail sometimes. It's going to get a negative reward, but it's going to gain something from the experience. So this is the same as like the labs that you're doing in XMLS. If you just give you the solutions, this is just SFT. You're probably not going to learn much. But if you let you experiment and fail and retry, then you're probably going to have a better learning experience. So take this with a grain of salt, because even though they did RL from the get-go, I don't believe that if you do RL on a model that has not seen any math, the model is going to be able to come up with proofs. That's not going to happen. The model during pre-training has been exposed to a lot of data that includes mathematical proofs. So the model has seen relevant information that is going to be useful to coming up with their own proofing strategies. Same thing with code. So there was this aha moment that they highlighted in the DeepSeek R1 paper, which was quite interesting. So this was for a mathematical problem. The model was trying to go into some path. It was not doing a lot of progress, but then it generated these words, wait. There's an aha moment that I can flag here. And then eventually it found the correct solution to this problem. Okay. So, so this actually shows some interesting property here. So the model tends to check its own work after deriving an answer. And this self-verification is something that emerges during the training process. Because if the model is working on a difficult problem, by checking the output, it ends up often going to the correct path to obtain the correct answer. And the reward is going to increase because of that. There is also a lot of reflection and backtracking that is verbalized by these models. Things like, wait, let me reconsider, things like that. And there is also this phenomenon of extended deliberation. For questions that are more complicated, the model needs to think for longer. And it can spend thousands of tokens, right? So not everything is nice here. So on the negative side, something that was noticed in the DeepSeek R1 paper is that the reasoning traces tend to have a lot of code switching between English and Chinese. Like it's not very consistent. Sometimes, not really interpretable. It seems to generate sometimes some tokens that don't make any sense, but somehow are useful to nudge the model to produce the correct answer in the end. And it's still not a solved problem. So there's just because the model can reason doesn't mean that the reasoning is clean. But one thing that they noticed here is that reasoning increases, that the quality, the accuracy tends to improve as models think for longer, as they spend more thinking tokens. And as you do RL for more steps, the average length per response also tends to increase, right? So both the length of the reasoning and the accuracy increase as you do RL. This also brings a challenge, right? That I mentioned in the first part, right? So you are going to have transformers that have to deal with very long context sizes. You need ways to do this efficiently. Okay, so the other point is the verifiable rewards. So the rewards in DeepSeek R1 are verifiable. We don't need a reward model as we do in RLHF. We don't need to train a reward model. We can use a regex, of course, this works with the math problems and coding problems, doesn't work for any kinds of questions. But the fact that they have verifiable rewards simplify a bunch of things. The RL algorithm becomes simpler, so they use GRPO, Group Relative Policy Optimization, which Zit is going to tell you about this afternoon. Yeah, and everything is simple. Okay, any questions before I finish? This is pretty close to the end. Yeah.
For what I was thinking is, yeah, this sounds amazing and we've known about it, but more about the side, is the reasoning text actually ever checked? And is there a way for us to verify if the model is actually using the reasoning text for a correct answer, or is it just guessing what we would want it to tell us as as a explanation for his answer? So is it actually giving any valuable input or trying to please us?
Yeah, this is a very good question. So I think the answer is I don't know, but there is some angle on this, which is models end up jumping to the correct answer because the thinking nudges the model in the right direction, not necessarily by the words that are produced, which is not necessarily because of the verbalization, but there are alternatives to producing reasoning tokens like this. There are models that try to have some loops in the transformer, to add more layers or to have like adaptive layers where they can spend more or less time instead of producing tokens, doing more computation in different ways. There is work with producing latent tokens that are not concrete words that are sampled, but representations that use some computation and nudge the model in the right answer. So my opinion on this is that I think part of the reason why this works is that models are able to use this extra compute in meaningful ways to increase the probability of the correct answer. But I think there is also something interesting that happens when you verbalize your reasoning. Maybe because it matches previous priors that the model has seen in previous mathematical proofs that end up, being effective. But I agree with you that you should not blindly look at the reasoning chain and believe that this reasoning is what led the model to ultimately it's all a bunch of matrix multiplications that are responsible for getting the final answer. I don't think we can add much more on top of that.
Thank you.
with a DeepSeek model, like, do they do RL only on code and math, and then this transfers like to natural language as well, or?
I think they at least they focus a lot on math and code. They might have done a little bit more, but they focus a lot on things that are verifiable. So for example, if you want to do, let's say, machine translation, then you're probably going to need some kind of reward model. You cannot use a regex to identify if a translation is correct or not, or general question answering. Things like multiple choice, I guess they could do as well, because they could match like the correct option of the answer with the answer that the model is providing. But I think they focus mostly, not just DeepSeek R1, but a lot of the work that has been done on reasoning, especially in the beginning, was focusing a lot on tasks related to math and code, which is a shame, because I think there's a lot of other problems for which reasoning is important that is not related to math and code. And it will be interesting to see how far models can go in those tasks. Okay, so all right, so okay, let me end the lecture by talking a little bit about what might be next. This is a bit speculative, or some things are already happening, so those are less speculative. So we are moving from tokens to action, right? So one observation is that LLMs, as I've described so far, they generate textual outputs for some inputs, but they don't intervene in the real world, right? And this contrasts with agents, right? Agents are able to perform actions that are based on observations, but that interact in the world, in the environment. And then they get a response from the environment, and they adjust what to do next based on that response. So there was already a talk by Eric Xing yesterday on world models that touch a little bit into this topic. And of course, there's lots of research going on, empowering LLMs to be able to perform actions, to do reasoning, to do planning, to execute tools. There's two perspectives. Some people think that the best way of doing that is to think about LLMs as a component of agent systems to help them reasoning and planning. The second perspective is that you can actually embed agentic capabilities directly in LLMs. I think we are a little bit closer to the second perspective in the sense of the agentic models that are being produced. And so typically, there are several components that you identify with this kind of models. You have the LLM per se that we already covered, but we also need to be able to do some planning, some reasoning. You need to handle memory. For example, past interactions that you had with a user, information that you have learned. You also have tools that you should be able to execute, because if you want to, I had these examples with math problems, but if you want to count how many apples, you should use a calculator, right? There is no, it doesn't make much sense to output tokens to achieve the correct answer, unless you are doing research and analyzing why models fail. But if you want to solve the problem in practice, it makes more sense to call an external tool and to use it. And so you can think of a bunch of different actions that involve tool call, interaction, responding to users, when should we ask questions to users, when we should assume something from users without asking, and so on. And then these things can interact either with the physical world, if you are working with robots, for example, or something like an operating system, a web browser, a mobile app, and so on and so forth. Right, so these are a bunch of components that you need to take into consideration. Something brief about tool usage. So one of the earlier models that enriched LLMs to be able to execute tools was Toolformer. So what they do here is they modify the training process of LLMs so that they prompt the LLM to try to answer questions by using tools that match the correct answers. And so by doing that, they are training the LLM to actually to do a tool call and what arguments should be passed and what not. And by doing that, they are able to right. This is the prompt that they use to generate this training data. But they are able to obtain a model that not just generates tokens, but can also execute external tools whenever necessary. And in general, for agent models, for many in many situations, reasoning is going to be useful, right? Because there is this example that comes from the Young's slides. If let's suppose that you have a robot that is cooking, okay, and while it's cooking, the robot sees that there is no salt anywhere in the kitchen, right? So how can this problem be solved? Maybe you could buy salt online, but maybe you want to finish cooking quickly. Maybe you can find a replacement for salt, right? This is something that we can encompass in a reasoning session. Like so, maybe soy sauce could be a good replacement for salt. So it's not always going to be the case, but maybe for some cases it works. And then it needs to define a goal and to start acting to achieve that goal, like where to find the soy sauce. Maybe it needs to turn right, see a cabinet, open the cabinet, get the soy sauce, and so on and so forth. So interleaving reasoning with action is important. There are several models that do that. React is one example. In some scenarios that are more complicated, if you have a complex goal that you need to break into intermediate sub-goals, you might need to have some kind of orchestrator that divides the task into sub-goals and coordinate with multiple systems. But the point I want to make before finishing is that these agent models can be used in a variety of different domains and environments. It will be interesting to think about the common denominators between all these different things so that we can do progress in building a good theory for this. So one classical example is coding agents. This is where current models are excelling. Many of you probably use Plot Code or something similar, and you saw that they can do amazing things. In this case, the environment consists of repos, file systems, IDEs. The observation space is code files, executable outputs, commit history, things like that. And then the actions that you can perform are editing codes, search for files, test some updates, and so on. If you are in the space of web agents or app agents, then the environment are browsers or apps. The observation space can be screenshots of what is showing in the screen, maybe the HTML coding of a page, historical actions that you have performed. The action space could be clicking a button, typing something in a box, scrolling, and whatnot. If you are dealing with the computer use agents, then the environment is the desktop operating system. The observation space can be, again, screenshots and a bunch of other things. And the actions are keyboard or mouse controls. And I could go on and on, right? So, if you are working with the physical world, we have robots that execute other kinds of actions and so on. So there's many topics that I could not cover in this lecture for lack of time, which I think, by the way, it's already past time. Okay, so things like retrieval augmented generation. I didn't have time to talk about this. I only covered tools and agents very superficially in the very end. Things like vision language action models, world models. We had a lecture yesterday by Eric Xing on this topic. I didn't cover details about pre-training and mid-training optimization, but I'm happy to talk to you about some of these topics if you are around. Evaluation is a very important thing. It's a shame that I didn't cover it. Sorry for that. But it's actually something that is extremely hard. There is no good way of evaluating models. You have benchmarks. Models saturate these benchmarks very quickly. You don't have good benchmarks for many tasks. So I would love to see progress on evaluation. And then there's topics that are going to be covered in other lectures. Zita is going to talk about RL. Desmond and Bruno Saturday. They're going to talk about multimodal LLMs. That's it. So this is my conclusions. I don't need to read these slides. Thank you very much. If you have questions, I don't know if there is time for maybe a couple of questions, not many, because you probably are hungry and want to have lunch.
Yeah, thanks a lot for the lecture. I just have one question around Euro LLM in general. I feel like there's maybe some discourse that Europe is kind of in a mixed state right now between the US and China, who are both like producing new models basically every week. So I'm curious what Europe's priorities are in terms of like the capabilities we want the models to have. Like, is it mostly multilingual or is it code or reasoning? What is it?
You mean the priorities in my own projects, in what you're doing here?
In Euro LLM or like
Okay.
in European AI generally.
Yeah. So the reality is that you have a lot of progress being done in the US and China. Europe is behind. We should be clear about it. The RLM is not at the same level as the most recent models that have been delivered. But so far we invested a lot on the multilinguality part, because that was when we started the project. The frontier models were not very multilingual. They lag behind if you don't use them in English. And I think we succeeded. So it's still a strong point of RLM, even though models became much better in speaking many languages. But now you want to bridge the gap with respect to the existing models, making these models multimodal, making them able of reasoning, and later as agents as well. So what we are doing right now is we have a computer location in Jupyter, which is part of AirHPC, where we are, several of my students might be seated here. They are looking at providing vision and speech as additional modalities, and we are doing very good progress on that. And making these models cope with very long contexts, a little bit like I spoke in the first part of the lecture, so that we can train them to do reasoning and start catching up with the other models, and trying to do everything in an open source way.
Thank you.
By the way, if people are interested in collaborating or helping in this space, I'm happy to hear about how you could help. So we have been doing these projects collaboratively, and if your interests overlap with this, we can talk. Any more questions? Okay, there is one more.
Thanks for your talk. And just a quick question. I've seen there was a bit of hype on this thing of in-context scheming of models from the Apollo research. So I want to know what your opinions are on that. And yeah.
In context?
Scheming. Like models deceiving when conflict of interest.
Yeah, so I mean, I didn't talk about safety. This was another topic that was left out here, but it's an important topic. Actually, I should have listed that in the list of things that were not covered. Yeah, there was like for example, recently there was an incident with the Hugging Face, right? So the OpenAI models were being evaluated in Hugging Face, and they found some vulnerabilities and were trying to, I don't know how much of this is made up or hype, just to emphasize how good and dangerous models are. But apparently they try to obtain the correct answers in the test set so that they could do well on these benchmarks. And I think we are probably going to see more of these problems appear more and more, because models that have agentic capabilities, they have goals. If there are goals, they develop strategies to achieve those goals. And that risk is always there. Yeah, I don't know if that answers your question, but I think it's a problem that you need to think about and try to mitigate it as much as possible, without blocking research. Europe has been focusing a lot on regulation, but sometimes this ends up making us moving too slow in this space. Regulation is very important. Safety is extremely important. So we need definitely people doing research in those topics, but we need to do it wisely, right? And this is one of the topics that, is anyone working on these problems, by the way? Safety, vulnerabilities? Okay. Yeah, so I guess you agree that those topics are important, and we need to look at them.
Thanks.
Okay. Enough for this morning. Great lunch.
All right. Huh? Okay.